Yeah, good morning, Arunjit here.
Yes, sir.
Am I audible?
Yes, sir.
Oh. Has Sukanya joined?
No, she has not joined yet. I'm just waiting for her to be.
You have dialed is currently busy. Please try.
Good morning to all the participants. There is an important announcement that I have to tell you that, as you know, today we had this is the last day of our AICT Atal Faculty Development Program. So after the lunch, we will have one more session from an industry expert, and after that, you will be having an assessment for 1 hour. It will include 30 questions related to our IoT and its applications. So 30 questions will be there. Time allotted to you will be of 1 hour. And then after that, we will have the valedictory function.
Sukanya, you are joining now?
So I just bring to you all know this, that we'll have an additional session today, extra session at after the lunch.
Sukanya is joining.
Okay, sir. Okay.
Yeah, she has joined.
Okay, sir. Sukanya ma'am, am I audible to you?
Yes. Right.
Yeah, yes, you're also audible. Shall we start the session?
Yeah, it's up to you. If you want to wait for another 5 minutes, then that's fine by me too.
Okay, ma'am. Thank you. Dear participants, again, there's an important announcement that I have to make, that today we'll have an extra session, another session with an industry expert, that is after the lunch at around 2:30. And after that, we will be having an assessment test for 1 hour, which include 30 questions. And then after that, we'll have our validity session. Test is compulsory for all. The text will in the form of in Google form. The link will be shared on the WhatsApp group or on the chat box of Zoom as well.
Time of test, at what time it will be?
It will be of 1 hour and 30 questions will be there.
will the results be announced immediately?
No, ma'am, that will not be announced. That you will be no, after later on you will get the result.
Exam will be after valedictory function, madam.
No. It will be after the third session. That is, after lunch we'll having a session. Then after that we'll having the exam for 1 hour.
Okay, madam. Thank you.
Okay. So Kanya ma'am, I think we'll start now. By the time all the participants will be joining. Okay.
Sure. Yeah.
Good morning to all the dignitaries, faculty members, and dear participants. I, Priyanka Saxena, welcomes you all in the last day of AICTE Atal Faculty Development Program on IoT and its application. Today, we have with us Miss Sukanya Mandal. She is a data scientist. She has done her BTech in Electronics and Communication and further education from Oxford University. Her skill sets include data science and artificial intelligence, cloud, AWS and Azure, Internet of Things and edge intelligence, machine learning operations, AI operations and containers, UN Sustainable Development Goals, team building, lead and team management. Her area of expertise is in the field of data science, machine learning, artificial intelligence at the edge, and Internet of Things. Thank you so much for accepting our invitation, ma'am, and we are really looking forward for your session.
Thank you, ma'am, for the warm welcome. Good morning to one and all. Did I share my screen now?
Yes, ma'am, you are the co-host, so you can share your screen.
Madam, when will we get the PPT of lectures?
Sir, I will answer all your
That we will
questions later on.
We will share the PPTs. We will share the PPTs after all the sessions by Monday morning. And
Madam, will we get the reading material or PPTs of the lectures?
the speaker, those who have consented to share their PPTs will be shared to you. And we will upload into the AICTE portal, the reading material as well as the PPT, we will upload it to the AICTE portal. From there, you can download. And also those who have consented to share their portal, their presentations, we will share individually, share it to you individually also by email. Okay. Is that clear? The content and the presentation will be shared to you. All the presentation, I am not assuring you that all the presentation will be shared. The faculty that who have consented to share the presentation will be shared to you. And your marks and all these things will be shared to the AICTE portal. From there, you can download it. And you have to also fill the feedback form at the AICTE portal by the end of the FDP. Then only your certificate will be generated. I will. Have you got? Am I audible?
Yes, sir. Yes, sir. You are.
Yes, sir. Yes, sir. Yeah. Okay. Sukanya, you can start.
Sure, thank you. So my screen is visible, I believe.
Yes,
Yes,
ma'am.
yes, ma'am.
Right. Great. So today we'll be talking about IoT and specifically the cloud and edge implementation scenarios. So we have two back-to-back sessions. In the first session right now, we'll be talking about IoT and how cloud and edge, especially where cloud and edge scenarios are best suited. And also at a very high level, we'll be covering some of these services provided by the major cloud providers. And at the second half of the session, we will cover all of those services, most of those services, at least for Azure and AWS, in depth. what each of those services do, and how do they cater to the IoT edge and cloud implementations. And once we have a fair understanding of how those services work, we will look into a few use cases of various connected applications like preventive maintenance, then connected home, predictive maintenance, all of these things. Okay, so to begin with, okay, let me know if you have any questions. Feel free to stop me in between, unmute yourself and you can ask, or else ma'am, you can also coordinate and let me know if there are any questions in the chat. I'll be happy to answer them. Okay, so starting off with IoT. So the difference between the classical internet and now the Internet of Things. Back when classical internet was just booming, somewhere around 1990s, right? Not many devices were connected to that internet, to that classical internet. With time, the majority of the classical internet has gone up, and now at present times we see a very matured model of internet, but the only limitations there is the classical internet pretty much uses just the TCP protocol to communicate, right? And of course it's for wide area networks, and any devices that is right now IP enabled and has the capacity to be connected over this internet with TCP protocol can be communicated from somewhere else on the earth. Now then there are certain benefits that happened with things getting connected on the internet. First of all, as I mentioned, communications at length from one place to another was possible because of internet. Then the data collected from these connected things over the internet could also give more insights on that, on the not just the device health, but also a lot more information that could be utilized to optimize further activities. Now, basis this foundation came the era of connected things. Now we are in an era where Internet of Things, I mean, we have been talking about Internet of Things as the hype a while back, like around 6-7 years from now. And right now, it has reached a certain maturity where we are seeing applicative use case. The idea behind IoT is to connect all the things over a network. It need not always have to be a TCP network. It can be your personal area network. It could be wide area network, like Bluetooth, and also it could be protocols. It could be over protocols like MQTT or LoRaWAN, which deals with larger scale transfer, but MQTT and LoRaWAN deals with much like internet, it deals with larger scale transfer, but it is specifically for embedded. It is specific to the needs of embedded environment because it is capable of catering to certain features that embedded environment of the IoT possess, right? So combining the physical things plus computing plus connectivity plus sensors plus actuators, we get IoT. So IoT is basically a network of ubiquitous things. When I say things, or when we say things for Internet of Things, things are basically anything that can be connected over this network, be it your refrigerator that you use at home, be it your home, be it hospitals, be it cars, be it trucks, be it your watch, anything and everything that gets connected, including us as humans. At some point of time, we are also, I mean, very soon we'll also be in this ubiquitous mesh of things, and we would be easily locatable. I mean, the way to locate us would be through URIs, or unique resource identifier, and the way to locate these things on over the internet is also through URIs. So why connecting everything, as we were talking about? So once we connect everything, connection of those things over a network, since IoT, the things in the Internet of Things are sensor enabled, those sensors can sense and collect informations from the surrounding. Now, once we collect those informations, and through this connectivity, we can pass all these informations to a compute infrastructure where these data could be essentially analyzed. The benefit of those analysis, initial analysis, is it helps us in real-time monitoring, or else just data logging as well. Connectivity helps us transfer this raw data to a certain compute storage or a server located elsewhere, and because of such transfer, it is possible to create a dashboard, and that could help us in real-time monitoring of those features. Now, beyond this monitoring, if you want to get a few more insights, then we can go into analysis of data. Analyzing those data basically helps us understand a little more about the data. Like it helps us understand the descriptions of the data. Not just that, it also helps us understand what's going on in the surrounding of those things where sensors are implemented. Now, once we have that understanding of what's going on, we can definitely leverage control on those things, right? Like if we understand that, okay, so let's say if your light, if the tube light in your room is connected, and with the help of data, you understand that there are no individuals currently present at the room, right? Then we can send a control action that could switch off the light, and we don't necessarily need to come inside the room. We can do that because of connectivity from elsewhere, right? So we can impose certain control actions that basically helps optimize the performance of those things. And once we can leverage those control actions, we can create values essentially, right? So when we say create values, as in we generate ROIs. We generate the real-time value of that IoT promises. So basically, physical things can sense, communicate, and collaborate, creating greater intelligence outcome to bring more value to the users or things. This intelligence at the end of the day is creating more values and helps us in generating more ROI. Okay, now talking about the benefits of IoTs, benefits are at two different levels. One is the benefit to the users, and of course the other is the benefit to the manufacturers or the administrators. So benefit on the user side is, we as a user, when we use IoT, Internet of Things, right? So in that case, we monitor and control those devices. We get to monitor and control those devices. As a matter of fact, once we can monitor and control those devices, we could use those devices efficiently without unnecessary utilizations of those utilities. Now, attached to this second benefit, when we are using those utilities efficiently, the service life of things can get extended. The service life of things gets extended, and hence we receive improved experience through collaborations of things, and of course the things are autonomous in nature, right? Why the service life of things gets extended? Now consider situations where you're using your fans, right? Now you're out of the room, you think that you'll be out of you'll just go in a jiffy and come back, and you keep your fans on. Now, once you go out of the room and let's say something else comes up, and then you forget the fact that your fans are running. In that case, your fans are just running without any needs, without any explicit needs. Now, that is not efficient utilizations of the resources, be it the device as a whole or the energy or the electricity that we are using, right? So if it is connected and if it is sensor enabled, the fan could sense that no one is in the room and could switch it off itself. Next, when you come back, it could actually switch on again itself, by itself. So that essentially procures usage of things efficiently, which further extends the service life of things because you're using it efficiently, and you as a user, your experience is also enhanced through collaborations of certain things, these kinds of things, and of course, as I mentioned, the device is autonomous on its own, right? Okay, moving on, the benefits to the manufacturers and administrators. So manufacturers or the administrators of those devices gets to get the real-time insights into the device locations, conditions, usage, and performance, which further opens new opportunities to monetize value-added services around product usage. So when I say which further optimizes, provides opportunity to monetize value-added services, that means let's just consider a scenario. Let's say a smart refrigerator. You've bought a smart refrigerator. Now that is capable of connecting over the internet and performance necessary actions. Now the device manufacturers, on the other hand, you have consented. You as a user have consented to provide usage logs to the device manufacturer. Now, when you have consented, the device manufacturer, post your consent, could keep a track of what's happening with the device. Of course, it does not know where things are located because at the end of the day, those data are kind of masked, but it still has an idea at the device level how things are performing. Now, let's say with continuous monitoring and analysis, the device manufacturer all of a sudden discovers that this device is not operating as it should. It's not operating optimally as it should. So what happens there is once the manufacturer realizes, and this realization, this decision, or this outcome comes as an impact of continuous monitoring of the device, right? So once they come to such a conclusion, what they could do is they could optimize the backend firmware or the software that is controlling the hardware, and send a patch over the air as in over the internet to this device. Now, once this patch is actually attached, installed on the device currently, then this patch is capable of optimizing the device performance. Therefore, this is how you can open new opportunities to monetize and value-added services. Also, not just fixing that's called, when a patch is sent, that's called fixing the current software scenario, right? But also with this regular monitoring of this devices, it is also possible. It is also possible for the manufacturers or the administrators to install more value-added services, or to basically push more value-added services over the air, so that let's say your battery of those devices is draining badly, right? Now, once they send this patch, your battery now starts performing at optimal level. Not just that, it could also understand when it is not required and could go on snooze mode. So this could be one of the possibilities. So the possibilities when things are connected over a network are endless, and it depends on manufacturers to manufacturers and administrators to administrators to basically understand and take the necessary actions depending on their product goals. So as I mentioned all this, I covered the last 2 points as well: ability to improve future products and in-field product upgrades for extended life cycles. Now moving on to the next slide, talking about various kinds of IoTs. We have consumer IoT, industrial IoT, civic IoT. Consumer IoTs are pretty much the ones that you use. Let's say your smartwatch, then telehealth or telehealthcare, any kind of healthcare devices that is basically connected, smart thermometers. Then your personal pet assistance and pet monitoring, the RFID tags that you just use, right, to keep track of your pets. Then the RFID car lock keys that you use. All of these comes under consumer. Anything that we as a consumer use comes under the and is connected comes under the consumer IoT scenario. Now, talking about industrial IoT. So in case of industrial IoT, manufacturing unit, any kind of manufacturing floor that is connected over the internet and is sensor enabled comes under industrial IoT. Aviation industry, smart home industry, healthcare industry, any industries, agriculture industries, weather industries, food and beverage industries, any industry that implements IoT comes under the industrial IoT sector. And civic IoTs are like, you know, your building management and your security cameras, then everyday things. All of these comes under examples of civic IoT. I mean, this slide is not necessarily differentiating between various kinds of devices, but it's just giving you an idea to understand where and how IoT is being applicable at present times, right? All right, moving on from there. Now, we talked a lot about what IoT is and specifically what could be the possible scenarios of IoT. Now, we need to understand what it basically takes to make IoT a possibility. IoT itself is a vast field and a horizontal field, which is a combination of various verticals. Each verticals requiring specialized skills of its own. So if you could see this slide, at the very beginning, we have IoT, which is an amalgamation of a lot of other things that is currently mentioned here. So starting from the very left, we have sensors and actuators. Now, when it comes to IoT, creating sensors and actuators requires very specialized electronic skill sets, and not everyone has that, right? So that's again a vertical of its own. Someone who knows how to design sensors and actuators. Then comes the brain, or brain that senses the inputs from the sensors and actuators, right? So for that, we have the single board computers or systems on chips manufacturers. Again, those requires very sophisticated electronic skill sets to even design such hardwares. Then comes the firmware part of those hardwares, something that controls those hardware, embedded programming. So embedded programming again requires very specialized skill sets because it's just one level up, one level above the general coding paradigm. So in case of this, in case of embedded programming, the developer would just not only need to know about coding or how computer programming works, but also needs to know about the hardware specifications and how each kind of programming can be implemented in each of those hardwares, right? So that's again another specialized skill sets. Then we have intelligent devices or mobile devices, which basically forms as the which basically acts as the IoT hub. Now, again, creating such intelligent devices or mobile devices requires specialized skill sets, because a lot of other things also comes into the picture when one has to create that intelligence within those devices. Then comes the internet or the connectivity part of it, that basically is responsible for transferring the data collected by those things or sensors over this network to a compute or a storage beyond for further actions on it. So that is where internet and gateways comes into the picture. Then we have the cloud computing paradigm, where I mean, previously it was mostly on-premise. Right now, because of a lot of troubles with on-premise infrastructure, which I'll cover in a while, most people have moved to cloud computing areas. And here, cloud computing again requires specialized skill sets to manage everything. And you could do a lot of operations and tons of tasks on the cloud computing itself. I mean, cloud computing could be used for storage, could be used for other modes of computing as well. Now, once you store utilizing cloud computing services, now the massive amount of data generated by disconnected devices gives rise to big data, or nowadays data in general. Well, big data, the term is subjective. Big data was back in 2010 or 11 or even beyond that, where because back then data was limited. Things were not connected. Even smartphones did not quite come into that existence as it is today, right? So then we had data, and subjective to that amount of data. Once we started receiving more like terabytes of data, then we termed it as big data. Now, in 2021, moving on to 2022, those kinds of data size is pretty much normal, and it's just data. So again, managing those amount of data, and not just managing, also managing and consumptions of those amount of data requires very specialized skill sets. That's where data engineers comes into picture, right? Then we have data analytics, where we utilize this big data to gain insights, the much needed insights into the scenario. So there we have data scientists coming into the picture. Then once we have an understanding of what's happening, once we have that information, we also want to generate knowledge out of it, knowledge out of those informations. There we have the artificial intelligence or AI engineers working together in unison, right? So all of these amalgamated together makes actually an IoT application possible. So how does cloud come into the picture? So at the very bottom layer, we have data. Then we have cloud, which basically forms the information layer. And then beyond that, we have knowledge. So if you see this diagram at the very bottom layer, we have data or the things collecting the data, right? So we have things that produces data, which is further connected to gateways, which receives control actions from cloud and forward those to things. And then those gateways act as a middleware that is responsible for sending the raw data directly to the cloud. And once those raw data are processed in the cloud sends some kind of control actions, and those control actions are again relayed from the cloud to the gateway, and the gateway again acts as a middleware to send things to the control actions to the things, right? So we have all of these working together. Cloud basically comes into the picture when we need data processing, storage, and other forms of compute needs. And then beyond that, once we could process all this information, all this raw data in the cloud, we send it to front end dashboard for remote monitoring and controlling. This is where knowledge is being generated. So you get the scenario where cloud comes into the picture right now. So we have things, then we just have a gateway, the internet or the gateway that passes those data to the cloud. Cloud is responsible for the entire compute, including storage, and then also sending control actions back to the things. And then we have the beyond cloud, we just take the output of the process data to a dashboard that is available to end users. Now talking about cloud a little bit, what is cloud? Cloud is basically a pool of virtualized computing resources. Cloud can host a variety of different workloads, including batch style backend jobs, as well as interactive and user-facing applications, right? Then also, in other words, cloud computing refers to a virtualized platform with elastic resources on demand by provisioning hardware, software, and datasets dynamically. Now, a couple of things to note from these two definitions is cloud is a pool of virtualized resources. We don't get to see those resources, but still we get to access those resources. Hence, virtualized. Any kind of workloads at this present time can be hosted on cloud. It is that matured, be it batch style or real-time workloads, and any kind of workloads can actually be uploaded to cloud. Also, cloud refers to elastic resources, wherein elastic means a couple of things at this when it comes to the context of cloud, which means that first of all, it can scale as per required, scale up and down on its own, or it gives you the provision to scale up and down depending on a requirement. When I say scale up and down on its own, that's the serverless computing paradigm, which we'll cover in a while. You as a user of those cloud resources, you have the liberty to scale up and down depending on a requirement. And also you just pay for what you use. Let's say you've enabled a virtual machine for 100 GB of volume right now, and you see 100 GB is not enough for you, you want to expand it to 200 GB. And in that case, you expand it to 200 GB, and you can do it just with the click of a few buttons. You don't need to worry about computing resources. It is provided to you on demand, and you just pay for those 200 GBs that you have utilized or that you require. And also, software as a service is something which I'll cover again in a while. So you also get to host software directly on the cloud and can just retrieve it from there, right? So those couple of things are pretty much possible on the cloud side, and helps you just focus on the applications rather than the infrastructure. Now, talking about a few, I mean, not just a few, these are the cloud deployment models, something that you should be familiar with when one is dealing with cloud. So one of the deployment model is private cloud, wherein we have the these are servers that are hosted within a single organization and is accessible by the members of those organizations only, not by anyone else outside the organization, right? So let's say you as an educational organization have a server of your own with capacity, with certain compute and storage capacity. So and you have all your organization's data stored on that server, and you perform all the necessary actions on that server on your privately hosted server, and that's it. And only members of your organizations with your organization's credential can access that server. No one outside or no one with a different credential can access that. This is a typical example of private cloud. Public cloud are the hyperscalers, AWS, Azure, GCP, DigitalOcean. So all of these clouds are public clouds wherein you could utilize the resources provided by these clouds to perform the necessary application actions that you would require. So anything and everything provided by these cloud providers, all of these services are open to public, and you can just utilize it basis the subscription model and depending on your requirement. Subscription model as in whether it's a pay-as-you-go subscriptions or a different kind of a subscription, right? Then you have hybrid cloud, which is a mixture of private and public cloud. So let's say to explain what hybrid cloud is, let's say you have a cloud, you have your private cloud, and you just are using your own data center of the private cloud for just data storage purpose. Now you probably need some analytics on top of the data, and you decide not to invest on your private server because that kind of investment is again huge. So what you just do is you choose one of the public cloud provider and just put the processing of the analytical workload on the cloud, and post analysis again the data gets stored back to your private data center. So this is an example of hybrid cloud wherein you are utilizing your both private and public cloud to make your applications a possibility. Then there is something called multi-cloud and hybrid multi-cloud. So multi-cloud is the utilizations of one or more public cloud. Sorry, multi-cloud is the utilizations of two or more public cloud. In multi-cloud, you don't just for multi-cloud you don't use private cloud, whereas hybrid multi-cloud is the utilizations of your private cloud plus two or more public clouds. Right? To put forward an example, again, let's just say in multi-cloud, how do I see this? Okay, let's say you are building an IoT applications, right? Now, depending on the application requirement, let's say you choose to provision the compute part of IoT, which is device provisioning, device registry, all of those things, which again we'll cover in the second half of the session. So all of those things, let's say you want to provision it using Azure, and you want to perform the AI part or the analytics part of it on AWS. So that's a typical example of using multi-cloud. And hybrid multi-cloud is, let's say, again, you have in-house data center. You want to, let's say, analyze the data using AWS capabilities. Now, post analysis, you don't push the cloud. You don't want to push the analyzed data to your local data center, but you would like to push the data to, let's say, an Azure storage. In that case, you are utilizing both your private data center, your and two or more public clouds for your application needs. So these are pretty much the essentials of cloud deployment models, and at present times you will see models of these kinds only. Now talking about cloud computing and who manages what. But before I move on to this, so far any questions? Please feel free to put it in the chat. I'll just take 1 minute of pause. Or you can also unmute yourself. Feel free to do that as well. Here's a question for you. Anyone currently focusing on building IoT applications on the cloud, or anyone currently using clouds per se for any other applications, not just IoT? Anybody? Yes, no, something. So no one is using cloud at the moment? Am I audible, by the way?
Yes, ma'am.
Okay, so I take it that no one is using cloud at the moment, correct? All right. So talking about, moving on, talking about cloud computing and who manages what. So, when it comes to cloud computing, as we were talking about, so on the very left-hand side, we have traditional IT, which basically resonates with the private cloud kind of a model. When it comes to traditional IT, on-premise systems, everything has to be managed by the in-house IT team. Networking, computing, storage, anything, even for failures, it has to be managed by in-house IT teams. Then came the paradigm of infrastructure as a service, wherein you see the blue lines that the providers of the public cloud manages, and the green sectors are managed by you as an engineer. OneDrive is a cloud application. Yes. OneDrive, Google Drive, all of these are cloud applications. So, okay. Ma'am, it says participants cannot unmute. Ma'am? Hello? Okay, I think I also had the permission to give all of you the permission to unmute yourselves. Can you give it a try, Supriya, ma'am?
Yeah, ma'am. I think now we are able
Yeah.
to unmute.
Yeah, wonderful. Okay, so do you have any questions?
No, ma'am. I was just like OneDrive. I'm using currently, right? So I was just so it's also a cloud application, right, ma'am?
It's a cloud SaaS, software as a service application. Basically anything that you upload on the on OneDrive gets stored to a backend cloud storage, and that's how you get to retrieve. But see, so whenever you require to use OneDrive, mostly you require internet, right? So and now nowadays they have also given the option to store an offline copy of it on the edge side, so that you can review it when you don't have an internet, right? So that's an applications of edge computing.
Thank you, ma'am.
Okay, now moving on from the infrastructure as a service module to a platform as a service module, wherein you see again the blue line, everything is managed by the cloud service providers. Only you need to take care of your data and applications. That's it. Now, from there on, moving on to the serverless paradigm, wherein you just need to focus on the application that you're building. And rest of the things are taken care of by the cloud service providers. And then you have software as a service where everything is taken care of by the cloud service providers. All you need to do is just go to your web browser, put up the URL, and you access it. That's it. Put up the when you're just hitting the URL, you're basically calling the service, and that's how you get to access it. Right? All right. Moving on. Any questions here on the infrastructure, platform as a service, serverless and SaaS? I also have another slide to basically go into the depth of things. So what happens here is, in case of software as a service, also known as cloud-based softwares or cloud applications. In this case, the entire software is hosted on the cloud, and you just use it via a web browser. So this is the typical example, right? Supriya, you brought up the OneDrive, Google Drive. All of these are examples of software as a service. Or you just get to use a dedicated desktop client and just utilize those software. And entire software is hosted on the cloud. All you just need is either a client on your local machine or just an endpoint to hit on the web browser to get access of it. Now, in most cases, software as a service, the subscription model is either you pay a monthly fee or an annual fee, or even sometimes some softwares and some providers offer pay-as-you-go model, which is you just, let's say you're utilizing the software for an hour, you just pay for that hour of usage. Now, platform as a service is something which provides software developers with on-demand platforms, such as hardware platforms, networking platforms, software platforms. All of these are most for the case of platform as a service, most of the things are managed by the cloud service providers, and you get to access those platforms once you just make a demand. Like when I say make a demand, that means that once you know that you would require, let's say, a virtual compute platform. In that case, you just go to your respective cloud providers and spin up a virtual machine. Right? Virtual machines are nothing but, let's say, your laptop running on a cloud server on a virtualized server that you don't get to see necessarily, but you still can access the resources. Right? So doing so, having platform as a service, it enables developers to execute, which is run, develop, and manage applications without cost, complexity, and inflexibility of maintaining the platform on premise. So it basically gives you cost optimizations opportunities. You don't necessarily need to bear the headache of something that you don't want to do. Just focus on your applications. There are certain complexities associated with it, and also maintaining the platform on premise is something that you would need to you don't need to worry about, because you're not having that platform entirely on premise. Right? So here, then in that case, you don't need to worry about the necessary engineering capabilities that you would require. All you just need to know is how to utilize that service and how to utilize your internet and web browser. That's it. And your job is done. Infrastructure as a service is provides basically on-demand access to fundamental computing resources, physical and virtual servers, also networking and storage over the internet on a pay-as-you-go basis. So in this case, it gives you the necessary infrastructure, compute infrastructure that you get to access over the internet on a pay-as-you-go basis. When I say pay-as-you-go basis, that means again, pay for what you choose. This kind of model also enables end users, like end users as in we as consumers of cloud, to scale and shrink resources on as need basis, right? So depending on your need, you could actually scale and shrink those resources, which reduces the need for high upfront capital expenditure. Or unnecessary on-premise or own infrastructures, and for overbuying resources to accommodate periodic spikes in usage. So you could scale up and scale down on need basis. Therefore, there is no need for investing right up front for the entire capacity that you won't be using maybe in the next 1 year. And also the unnecessary on-premise own infrastructure need is eliminated from that. And if you basically have to, if there are periodic spikes, like let's say you are using capacity A of resources today, and tomorrow due to some reasons the need for that capacity increases, then on that case, since these are elastic by nature, that means it will scale up and down on its own depending on the compute capability required at that particular time of processing. Then you have serverless computing, which is also simply known as serverless, is basically a cloud computing model that offloads all the backend infrastructure management tasks like provisioning, scaling, scheduling, patching to the cloud provider. Just this ensures that the developers can focus on their much needed applications than anything else, right? And then you have function as a service, or FaaS, which is ideally a subset of serverless computing. Here in this case, it allows developers to execute a portion of the application code, or when you generally code, you have something called functions, which are reusable modules for various needs. So function as a service basically allows developers to create those functions in response to specific events, which gets triggered whenever you need to perform those specific tasks. Everything besides the code, which are the physical hardware, the virtual machines, the operating systems, as well as the web software management, is provisioned automatically by the cloud service provider in real time as the code executes, and of course it's spun back once the execution is completely over. Now, your build, when the execution starts, and your billing stops when the execution stops. Okay, so so I hope all the cloud computing deployment models are clear at this point of time. Feel free to ask me any questions if you have at this point of time before I move on to the next topic.
The second category, like the platform services, the difference between platform and infrastructure is just that in platform, like the scaling is not level. Is it so? Because both provide infrastructure.
No, not quite. Platform means a little different than just the infrastructure. So let's say when you're using IoT on Azure side, Azure provides you a lot of services that essentially acts as a platform for your IoT needs. Like we'll cover those services like IoT Suite. Inside that IoT Suite, we have IoT Hub, IoT Edge, then the entire Azure IoT Central, and then the data factory part of it, and all of these are services which are pretty much native to Azure. Now, combining these services, you basically create a platform for your IoT, right? For which basically are utilized to run as well as develop and manage your applications. infrastructure is pretty much the compute infrastructure that is required. Let's say for networking, you would require gateways and other kinds of servers, right? So that's an infrastructure that is already hosted on the Azure data centers. All you just need to do is utilize that infrastructure and perform the networking on the Azure side. So this is all about infrastructure. Even virtual servers, right? So those are present on Azure data center. You pull up the virtual computing resources and you access that. So that is infrastructure. Your storage also requires certain set of infrastructure. Like, let's say you use hard disk for your needs. That's an infrastructure for you, right? So those kinds of things are already situated in the data centers, and you utilize it as a front end that the cloud service providers gives to you. Whereas a platform is an entire software stack or an end-to-end platform combining of various services that enables you to perform that necessary application. Was this clear?
Yes, ma'am. Thank you. Could you please elaborate more on serverless services? Like serverless means
Well,
I couldn't get that clearly.
Okay, so you did not get the entire concept or any specific things?
It has a particular infrastructure, right? So it offloads all the backend infrastructure management. I did not get that particular point.
Okay, so serverless is a computing paradigm, right? So like when I say computing paradigm, as in serverless, what happens is you just pay for what you use. Let's say you have a data analytics end-to-end workflow hosted on cloud, right? And you have enabled that application to run in an entirely serverless mode. So ideally, I mean, when it's serverless, it does not literally mean that there is no server associated with it. There is a server, but the reason for it being called as serverless is because when you run that application, you're just only utilizing the resources when you run that application, not otherwise. Like your application is just there on the cloud, you don't incur any charge. But when you process and run those applications, you incur charge. So that is what serverless is all about.
Okay, got it, ma'am.
Yeah. Okay. Anybody, any other questions? Okay, so moving on to the next topic of IoT challenges. So in case of IoT challenges, there are a couple of challenges as very minute hardware and software gets connected over the internet. One of them being security, and along comes with security the privacy challenges. Then there is interoperability, and there is over-the-air upgrades, huge data volume, which of course I'll cover in depth. Then there is real-time actionable insights, complex event processing, standardizations, of course. So talking about security issues, now IT itself has its own security issues. Now with time, the IT security has matured over time, right? Now IoT is bringing in another layer of complexity to the existing IT scenario. So when I say IoT is bringing in another layer of complexity, it essentially means that all the things, all those minute things that are getting connected over the internet, all those hardwares does not necessarily come with security features enabled. Now, at this present point of time, your laptop is an IT requirement, right? So at this present point of time, with the enhancements of the system on chips or the processors that your laptop is currently carrying, it has, it has matured to an extent where there is hardware level security as well. And then beyond that, we also have the software level security. Now, since IoT is booming and is maturing and is still in its nascent stages, therefore, in most of the hardwares, we don't see SoCs that comes with hardware level security. Also, the softwares that are currently used in IoT does not necessarily come with proper hardware level security. Also does not come with embedded firmwares. It is difficult to instill security within those embedded firmwares as well. But of course, where we were back in 2015 and where we are now in almost 2022, the scenario is a lot different. Securities in case of connected things has improved vastly, but still not to an extent where we could say that security concerns can be eliminated. So therefore, a lot of researches are also going on in current times in terms of securing hardware and softwares when it comes to IoT, and also securing data transfers when it comes to IoT. Now, privacy is another major concern because your IoT devices deals with a lot of personal vital information. Let's say your smartwatch deals with a lot of personal health information, a lot of private health vitals, which you necessarily would not like to be exposed to over internet, right? So privacy is a concern, is a major concern, which is being addressed day in and day out, but of course requires more work. Interoperability is another challenge, wherein, let's say you are using hardware and firmwares provided by one service providers. Like, to take an example, let's say you're using NVIDIA, the hardwares and the softwares provided by NVIDIA. Now another sensor network is using hardwares provided by Samsung. Now there needs to be interoperability between these kinds of hardware firmwares, so that data can be seamlessly transferred and each of these devices is able to communicate on its own. So interoperability is something that is being worked on majorly. Then there is over-the-air upgrades. Of course, because of connectivity, you can just push an update over the air. Huge data volumes, I'll come to it. But before that, real-time actionable insights. The principle of IoT is to have real-time actionable insights. I mean, to have insights right there, right now. That is exactly where IoT comes into the picture. So real-time actionable insights require certain compute infrastructure, and that is where IoT comes into the picture. Then, and that is why it's a challenge, because even some applications could not even afford latency of greater than 1 second. So that's a challenge there, right? Then there is complex event processing, because events are sequences of actions that happens in the surrounding. So there is a need for those complex event processing in the term of code to tackle all of these complex events and process those, and that requires another set of expertise altogether. So of course there is this ongoing challenge, standardizations of a lot of things, of data, standardizations of protocols, standardizations of security. All of these comes into the picture. And then we have huge data volumes, which are data intensive. Okay, so when it comes to IoT generates massive amount of data volume day in and day out. Therefore, the task is quite data intensive, and you know, and to transfer and store all those data requires poses a lot of challenges, which we'll see in the coming slides, and that is exactly where edge computing comes into the picture. To give you an idea of how much data it is possible to be generated from these IoT systems, let's take an example use cases. Let's take a look at the example use cases. An autonomous car or a connected car is capable of generating 4 terabytes of data per day per car. Let's say each car having 200 plus sensors or cars. Then you have manufacturers, 10 TB of data per day per well. So there, in an oil rig where sensors are implemented, it's capable of generating 10 TB, even more, like 10 TB just for one oil rig. Now, if you have multiple oil rigs, you get the idea of the amount of data getting generated. Weather sensors, 5 petabytes. Petabytes is like we have kilobytes, then megabytes, then gigabytes, then terabytes, and then petabytes. Okay. Then aviation industry, 6,000 sensors in one airplane, generating more than a terabyte of data per day, 2.5 TB of data, 2.5 TB. I mean, these are just hypothetical examples, and it depends on how long these sensors are also being utilized. It could even reach up to 5 terabytes. Wind sensors, those are capable of generating 5 terabytes of data just for one such station. Now understand, if there are multiple windmills, located, then in that case you get the idea, right? Then you have ships, 1.5 terabytes of data per day, connected data, 1.5 terabytes of data per day, right? So this is the amount of data that IoT generates day in and day out, and it is essential to address these data challenges, high data volume challenges as well. So just before moving on to that, a little bit of thing that you need to know is, when it comes to drawing insights from those data, at the very bottom there we have raw data. Beyond that, we analyze those data and get the information out of it. And beyond those analysis, beyond those informations, we get the much needed knowledge, and then the wisdom. So knowledge is the AI window. So this is how we obtain meaning and the much needed wisdom from the raw data. Then on the right hand side, we have various types of analytics. One is the descriptive analytics, which is basically just, let's say you have your raw data, you perform some basic level of processing on this raw data, some kind of basic analysis, and you get an insight on what this data is all about, right? So that is descriptive analytics. Diagnostic analytics is you dig in a little deeper and you try to understand what the data is trying to say, right? So that is diagnostic analytics. Then predictive analytics is where you try to predict or forecast what is going to happen. Once you have an insight on what's going to happen, prescriptive analytics is something where you try to analyze what, if we change something, how is it going to impact? Can we once you have that prediction in hand, you try to analyze, okay, so how can we change or modify that impact that we are currently getting in the form of predictive analytics. So that is what prescriptive analytics is all about. Then we have, so the insights in case of centralized cloud flows like this, we have covered this diagram. So we have things, gateways, which are responsible for sending in raw data to the cloud. And then the cloud sends in the control actions. And then beyond that, we have the knowledge. Like once the data is processed in the cloud, it is passed on to a web client or a dashboard, a web dashboard, wherein we get to monitor and derive real-time knowledge out of it. Right? Now, why this? Now, data processing in case of such larger volumes and in case of IoT, especially for the sensor networks implemented at a very remote location, poses a lot of challenge, right? So in that case, these are the challenges wherein we have to deal with insufficient bandwidth. Like if the data has to be directly transferred from these things to the cloud, the data has to actually have to travel to a lot of distance, right? And hop through a lot of network. Now that basically brings in these kind of challenges wherein we could face issues of insufficient bandwidth, then intermittent connection failure. And since those things does not come with large storage volume, therefore data is perishable, data will get overridden or get deleted. Then because it has to hop through various networks, the latency of those data between those things in the cloud, latency of the transfer, latency is the delay of the transfer of this data to the cloud, is quite high, in fact, very high. Then because raw data is directly being transferred over network, the security, there are security and compliance issues because you are just sending in raw data without any kind of protection, without any kind of encryptions or any kind of protection. Then because of this latency, you fail to get real-time insights, right? So therefore you don't, I mean, basically if you don't get in real-time insights, there is little value of your entire IoT device, because the general principle of IoT device is to get real-time insights, without which, I mean, IoT sensor networks are implemented at a location where humans cannot reach. So if you don't get real-time insights, then in that case, there's no benefit out of it, right? And hence, as you don't get any real-time insights, you don't get to perform necessary actions immediately there itself. So there's a lot of delay associated with it, and hence it does not yield the real value. That's where edge computing comes into the picture. So on the left-hand side, we talked about this cloud computing paradigm, wherein the things are directly transferring the raw data to the cloud. And now, because of the challenges that we saw here, we provide an edge computing solutions in between the cloud and the things. So edge computing basically forms decentralized mode of processing. It moves the processing close to the data sources, and it selects the data and insights flow to the cloud. So basically what happens there is you have the things, and that thing passes the data to the edge. Edge does the initial level of processing and then sends on the processed data to the cloud. So basically there's an intermittent layer between cloud and things that is responsible for taking care of all the challenges that we mentioned here. And the edge is basically closer to the device. So therefore, the device senses things and just dumps it to the edge. Edge comes with certain amount of compute that is necessary to do the processing. And beyond that, once it will process the data, it just sends the processed data to the cloud. Okay, next we have is the things to cloud continuum, how things happen. So at the bottom there, things generate data. So then it passes the edge is responsible for real-time actions. So fog and edge that you are seeing right now. So when we'll cover hyperscalers cloud applications, it's pretty much has divided itself into cloud and edge. Cloud and fog and edge together comes in the paradigm of edge computing. So here what's happening is the device senses. So the way it's happening is if this, then react. At the edge layer, if it then says if this, then just act. Fog layer, if this, then improve. So both of these, if this, then improve, and if this, then act, are happening at the edge computing layer. And here at the cloud layer, more insights, because cloud is responsible for storing all the history data right from the beginning till date. And that is how you utilize all of those essential data to generate machine learning predictive insights. So that is exactly why it says if this, then you can plan for the future, right? So edge, fog, and cloud is how things happen. Basically, fog connects cloud to the edge. From an academic standpoint, if you have to differentiate fog and cloud, this is how it goes on. And again, from an academic standpoint, cloudlets was a term basically defined by Satyanarayan et al. Back in 2019, back in 2009. So they took the case, in the paper was about the case for VM-based cloudlets in mobile computing. In this work, they focused on latency issues. So this paper basically proposes a two-tier architecture. The first tier is known as cloud, which essentially deals with high latency. And the second one is known as cloudlets, which basically deals with lower latency. The cloudlets basically are decentralized and widely dispersed internet infrastructure components. So they are centralized and are distributed across the regions, and their compute cycle and storage resources can be leveraged by nearby mobile computers. Moreover, a cloudlet only stores a soft state, such as cached copies of the data. Fog computing seamlessly extends cloud computing into edge for secure control and management of domain-specific hardwares, softwares, and standard compute storage, as well as network functions within the domain, and enable secure as well as rich data processing applications across the domain. So again, from an academic standpoint, if you really have to differentiate all of these, this is how these things work together. But from a practical standpoint, it pretty much comes under the umbrella of edge computing. Again, this is just an academic differentiations. I'll just pause a minute. If you want to read through, go ahead, read through. And yeah, also, if you have any questions, feel free to ask.
Hello.
Yes.
Ma'am, one thing here, like gates are basically interfacing boards, or you can say like Raspberry Pi, etc. Am I right? Ma'am?
Can you repeat your question? I'm sorry, there was a background.
The gates which we were initially talking in cloud computing, they'll be basically interfacing devices. And like, so in addition,
you mean the gateways, right?
Gateways, right?
Yeah, so gateway devices are internet-enabled devices. Yeah, I mean, if you are if you are working on a POC, then ideally a Raspberry Pi is capable of getting connected over the internet. So when you connect sensors to your Raspberry Pi, even the Raspberry Pi helps gives the much needed, brain power to access data from those sensors. And also at the end of the day, Raspberry Pi is since being a microcomputer, it also has those chipsets in place that could basically transfer those collected data from the sensors to the cloud.
So ma'am, in edge computing, so in addition to Raspberry Pi, you would require more amount of hardware and software, or only will it do with the software too? Like if you are moving from cloud to edge computing, so in addition to that, you will also require some hardware and software.
Right.
In
You
addition
would,
to gateways.
yes, yes, you would require that. I have those slides. I'll just cover it in a bit. The enablers of edge computing, basically. So it varies from scenario to scenario. The one that you mentioned is more of a POC scenario, but consider a scenario where you have oil rigs, right, deployed, or let's say a steel factory that is having a sensor enabled. So the edge computing scenario kind of varies from those scenario to scenario, but by principle, the edge computing principle remains the same, right? Which yeah, I'll just elaborate on those in just a bit. So for computing from cloud to edge, I mean, these are just some of the technicalities that is essentially differentiating, but then again, all of these can happen at the edge layer itself. And cloud computing, of course, as we covered, is responsible for all of these, right? Then examples of edges, power grid, mobile networks, all of these are examples of edges where they have multiple points of presence, and then they have intermediate nodes managed by business, also can leverage as fogs or edge devices. Then we have smart cities, which also leverages edge computing. And then we have factories, oil rigs, ships, and aircrafts. So the on-premise infra managed by business, no direct access to intermediate network nodes, and extreme weather conditions. All of these are examples of edges. Your manufacturing factories, your oil rigs, your ships, and your aircrafts, all of these are typical examples of edges because a lot of processing happens here at the edge layer rather than just pushing everything to the cloud. Because let's say when your aeroplane is flying, it is not always possible to connect to the cloud, right? So a lot of things actually happens on the edge side itself. Now, one thing to note here is edge does not replace cloud, it simply complements it. So edge and cloud works together in unison. It does not work without each other, and cloud computing is responsible for the heavier workloads, whereas edge computing does the much needed initial workload to make an IoT application possible. Now, future of computing, intelligent cloud and intelligent edge. So basically, the intelligent cloud is an ubiquitous computing which are enabled by the public cloud and artificial intelligence technologies for every type of intelligent applications and systems that you can basically envision. The intelligent edge is a continually expanding set of connected systems and devices that gather and analyze data close to the users. The data, or both. Users get real-time insights and experiences delivered by highly responsive and contextually aware apps. Combining this with the virtually limitless computing power of the cloud with intelligent apps and perceptive devices at the edge of the network, you basically can create a framework for building an immersive and effective business IoT application. All right. Therefore, edge and cloud always have to work together in unison. Now, the advantages that are provided here because of edge computing is, so since initial level of data processing is done at the edge, therefore, while sending to the cloud, the data size becomes smaller because it sends only the insights. Then we have the nearest compute capacity leveraged, wherein therefore the challenge for intermittent connectivity is eliminated. Then we have perishable data, wherein you process things. So this challenge is eliminated because you process the things closer to the devices. Therefore, basic level of insights are already generated closer to the device. then because things are being processed closer to the device, the high latency is in transmitting all the raw data is eliminated, and edge computing basically enables us to experience those low latency requirement of the application. Then data stays at the source, only the insights flow. This is a very important point. So the raw data is already processed at the edge, so therefore raw data stays at the source. Only the insights flow, only the processed data or encrypted data just flows. Therefore, eliminating the needs of security and compliance. Then you have near real-time decisions, which basically eliminates the need of, because of all the previous things that we just discussed here, we get near real-time insights. Therefore, which eliminates the challenge of delayed insights. And we have, and because we get near real-time decisions, we get to have instant actions possible. Therefore, the delayed actions challenge is also eliminated. So this basically makes a full-fledged IoT device, IoT application possible. So this is where edge computing plays a major role. This is how edge computing plays a major role when it comes to IoT applications. Now, talking about the enablers of edge. So the enablers of edge are, edge requires driving more compact as well as powerful converged solutions. So processors and accelerators are one of the enablers of edge. Then we have micro data centers. Then we have converged systems, which are compute plus storage plus network. Then advanced systems on chips, which are powerful enough to run full-fledged operating systems plus complex algorithms. Then we have 5G, SDN, as well as NFV. Then we have complete edge software stack with analytics and machine learning libraries. So here, talking about the processors and accelerators, processors and systems on chips. So these are the processors and the systems on chips that are currently enabling edge computing, and also we are seeing more advancements of these, and in the coming years we'll see more chipsets such as these emerging in this area specifically, that focuses on low power utilizations yet giving high compute utilizations, right? So these are some of the enablers of edge processors and SoCs. Then we have accelerators like your GPU devices, your FPGA devices, that acts as an accelerator and helps you enable much faster processing at the edge, right? Then you have converged infrastructures such as these, which basically does the heavy lifting. So in this case, compute, storage, network, and virtualization components are grouped together in a package. These are much compact in size and are very much durable and are developed keeping harsh edge conditions in mind. Then these are optimized for low energy consumptions, and these are engineered to optimize performance and cost, and are ready to just be utilized right out of the box, right? Then you have compute for things to cloud. So you have microcontrollers, of course, which are small size, low power, and deals with low cost. Then you have systems on chips, which are server class SoCs with ARM or Intel. Then you have the gateways, which again has various configurations of its own. Then you have servers, which deals with again, which also enables those edge computing capabilities closer to the devices. And you have micro data centers, which are also enablers of edge. Micro data centers are small data centers, but small but complete data centers, right? Which also comes in various shapes and formats with various computing capacities. Then we have data centers at the edge. You have micro data center, which are standalone rack level systems, which contains all of traditional data centers in one box and designed for a specific set of workloads. Modular data centers. A modular data center is connected to the power grid at an utility substation. So modules can be shifted to be added, integrated, or retrofitted as required. So something like these are modular data centers, which are again closer to the, let's say, power plant or oil rig or whatever it is. Then you have portable data centers, where these are portable modular data centers, which contains the complete IT infrastructure in a shipping container. So these are also enablers of edge. Now next, we'll be talking about the cloud service providers. Before that, before we move on to this topic, any questions so far? Okay, so for cloud service providers, we have the hyperscalers, AWS. Yeah, is there a question?
काय नसतं काउन्सिलिंग केलं त्याला त्याला एक कसं होतंय ते डोमिसाईल नाही ना.
Yeah. Okay, so cloud service providers, you have AWS, Azure, and GCP. So on the Azure side, provides a couple of services like Azure IoT Central, which accelerates the creations of IoT solutions. In the next session, we'll look into these services in depth. For now, I'll just cover at a very high level, and then we'll take a break, and then we'll come back to the next session. So what happens here is you accelerate the creations of IoT solutions using Azure IoT Centrals. Then you have Azure IoT Solution Accelerator, which provides customized solution templates for common IoT scenarios. And you have Azure IoT Edge, which extends intelligence from the cloud to the edge devices. Then you have Azure IoT Hub, which basically is responsible for connection, monitoring, and controlling billions of IoT assets. Then you have Azure Digital Twins, which creates a digital model of your physical space or assets. Then you have Azure Time Series Insights, which explores and gains insights from time series IoT data in real time. Then you have Azure Sphere, which basically builds and connects highly secured MCU-powered devices. We have Azure RTOS, which is making embedded IoT development and connectivity easy. RTOS is real-time operating systems, and Azure SQL Edge, which consumes the services privately on Azure platform. Talking on the AWS side, we have at the device layer, we have free RTOS and AWS IoT Greengrass. So free RTOS is basically operating systems for the microcontroller, much like Azure RTOS. RTOS is basically an open source software, and Azure and AWS are having their own flavor of this RTOS. AWS IoT Greengrass is responsible for enabling the edge computing capability from the AWS side. And this lets you run local compute, messaging, as well as data caching, syncing of data and machine learning inferences capabilities on connected devices in a secure way. Then you have connectivity and control services, wherein you have AWS IoT Core that lets you connect device easily and securely, as well as interact with cloud applications and other devices. Then you have AWS IoT Device Defender, which continuously monitors and audits your IoT configurations to make sure that they aren't deviating from the security best practices. Then you have Azure AWS IoT Device Management. So AWS IoT Device Management makes it easy to securely register, organize, monitor, and remotely manage IoT device at scale. Analytics services. So you have on the AWS side, you have AWS IoT Analytics, AWS IoT SiteWise, IoT Events, and Things Graph. IoT Analytics basically is utilized to run sophisticated analytics on massive volumes of IoT data. Then you have AWS IoT SiteWise, which makes it easy to collect, organize, and analyze industrial data at scale. Then you have AWS IoT Events. So AWS IoT Events basically makes it easy to detect and respond to events from large number of IoT sensors and applications. And IoT Things Graph basically makes your life easy to connect different devices and cloud services to build an entire IoT application. On the GCP side, just native to IoT, we have Cloud Core, Cloud IoT Core, and HTPU. So IoT device management, integrations, and connections services. HTPU basically are ASIC designed to run ML inference at the edge. TPU is sensor processing unit. It goes one level up GPU, and it's a hardware compute accelerator provided by Google itself. And alongside that, you can use rest of the existing Google services like Dataflow, Publish, Subscribe, IoT Core, BigQuery, Vertex AI, etc. to basically combine with this GCP IoT services to make your IoT applications possible. So this concludes my session 1 for the day. I will cover all of these services, mostly for Azure and AWS, in depth, along with use cases in the next session. So for now, if you have any questions, feel free to ask, or else we can gather back in at around 12:10 and begin with the next session. Any questions so far?
Participants, if you have a question, please ask. You can unmute yourself or write in chat box.
Yes.
All these computings will be based on machine learning. All the softwares, like all the things would be working basically on machine learning models.
No, not necessarily. Machine learning only comes into the picture when you have to perform analysis or predictive analytics, particularly on the IoT data. But before that, even provisioning of IoT requires general IT capabilities. Did you get this point, by the way?
Yes, thank you, ma'am.
Okay. So what I meant to say is, when I say computing capabilities would be depending, there are various layers to IoT, right? As we covered in a couple of slides before, like this one. So until this one, until here you have the application layer of IoT. So to provision, here comes the IoT hardware, software, sensors, everything. To provision this, you would require the general compute capabilities. Then you have the network capabilities wherein you need to deal with various IoT protocols. And then here, once you have the data coming to the cloud compute or compute storage, then you have the data to be processed. And this is where analytics or machine learning comes into the picture. Make sense for it?
Yes, got it.
Yeah. Go ahead. Okay, so in case there are no other questions, we break for now then, and we'll gather back at 12:10 again, and we'll continue with the next session.
Thank you. Sure, ma'am.
Thank you. Yeah, so I'll stop sharing my screen and and do I need to drop off or can I just go on mute? Because
you
I
can
think,
go on mute, ma'am.
yeah.
Go on mute.
Dear participants, we'll have a short break and we'll meet again at 12:10. Dear participants, attendance link has been shared on the chat box. I request everyone to please fill the attendance of session 1.
Hello. Hello. Ma'am, if you're there, should we start? Hello, am I audible?
Yes, ma'am, you're audible.
Can we start, ma'am?
Yeah, sure, ma'am, sure.
Is everyone here, by the way?
It's been informed in the group, ma'am.
Okay. Okay, so just give it another minute and I'll start, yeah?
Yes, ma'am.
Okay, so let's begin. In this session, we'll be talking about the cloud provider services in depth, more specifically about Azure and AWS IoT offerings. And then we'll see a couple of use cases, how those offerings have been utilized in making those use cases possible. Okay. So start with, again, any questions from the previous session so far? Any concept that was not clear? Okay, so in that case, I believe everything was clear, and then therefore I'll move on. So starting with Azure IoT. So what is Azure IoT? Azure IoT is basically a collections of managed, Microsoft managed cloud services that connects, monitors, and controls up to millions of IoT assets. Okay. So it provides managed services for connecting as well as monitoring and also controlling millions of IoT assets. In simple terms, IoT solutions is actually made up of one or more IoT devices and one or more backend services running in the cloud that communicates with each other. So for this, there are three components. One is the IoT device component, the second one is the communication component, and the third one is the backend service component. So for the IoT device component, IoT devices are generally made up of electronic circuit boards, which have sensors attached to it as well as actuators, and basically which are able to connect over the internet. IoT devices includes some form of radio mechanisms to connect to the internet, such as Bluetooth or Wi-Fi devices. Pressure sensor or temperature or humidity sensors, even accelerometers are some of the typical examples of IoT devices. They capture information. Ma'am, do you see my screen, the PPT, Azure IoT?
Yes, ma'am.
Yes, ma'am, it's visible.
Okay, fine. Okay, so what happens there is, let's say, okay, so these devices captures the informations about a specific environment where they are located. For example, an accelerometer could basically indicate whether the elevator is at rest or at motion, right? So this at a high level are what IoT device is all about. Now then comes the communication layer to IoT. So basically the devices that we spoke about can communicate with backend services in both the directions, and it ideally needs to communicate with the backend services in both the directions. The devices may send the data to the service. It may also receive an indication from the service to indicate the frequency of the data collection. Communicating with IoT device also has some additional considerations. For example, IoT device may have limited power and connectivity and may be slow or intermittent, right? Then there is backend services. The backend service basically receives telemetry data at scale from the device and determine how to process and store the data. They also communicate with the device and manage the device lifecycle by controlling and monitoring the state of the device. Azure IoT, so this is backend services are basically the backend compute infra that is not just compute infra, the backend part of the application, like let's say your database services or any other services that basically is hosted on the Azure cloud. So Azure IoT suite entirely consists of IoT devices, the communication of those IoT devices between those IoT devices and the backend services, and finally these backend services altogether, right? So moving on, how Azure IoT works. So in case of Azure IoT, just a recap of the basic cloud computing paradigm that we just described in the previous session. So cloud computing basically involves delivering hosted services over the internet. Hosted cloud services are divided into 3 categories, such as infrastructure as a service, platform as a service, and software as a service. Infrastructure as a service provides virtualized computing resources over the internet. Typically, these are hardware resources that are deployed in the data centers. Examples of such infrastructure as a service basically includes storage backup and recovery services. PaaS services also are concerned with simplifying the software development. PaaS or platform as a service could provide services like version management and testing. Also, platform as a service provides a framework for developers to build and deploy cloud-based applications very quickly. In case of the software as a service, the software is basically centrally hosted and managed by the cloud provider. The end user uses the software as a service. Infrastructure as a service, platform as a service, and software as a service are ideally built on top of each other. Infrastructure as a service needs the most management from end users, and software as a service needs the least management from end users, right? Then what we have is, in case of Azure IoT product portfolio, it basically presents 2 kinds of paths for creating the solutions. One is PaaS and SaaS solutions, and the other is PaaS technologies. So when it comes to PaaS solutions, so Azure IoT Solution Accelerators, one of the services provided by the Azure IoT suite, is customizable PaaS solutions for specific industry verticals. IoT Solution Accelerator provides pre-built solutions that can rapidly be deployed within a vertical. Examples of IoT solution accelerators could include remote monitoring, connected factory, predictive maintenance, as well as device simulations. Software as a service solutions are suited for organizations with fewer device models, more predictable scenarios, and limited IoT or IT capabilities. So if you think of building an IoT applications and you know that you don't have enough human expertise on the IoT or IT side, and you are dealing with just a number of devices with more predictable scenarios, then in that case, software as a solution, software as a service solutions is the best case scenario that you could go with. Azure IoT Central is a managed SaaS solution which allows you to get started quickly with minimal IoT experience. IoT Central is suited when the IoT needs are straightforward and relatively little cloud deployment expertise is needed. So that is when you go for IoT Central. Yes, IoT Central, and also IoT Central gives you managed SaaS solutions, right? Now, when it comes to platform as a service technologies, so platform as a service technologies provides granular option to control all aspects of your IoT solution, which further enables you to create a fully customized solution. You can classify Azure PaaS technologies into 4 categories. One is device support, the next is IoT, third is data and analytics, fourth is visualization and integration. So talking about each of these in brief, device support, what does this do? So Azure IoT provides various means to support a range of devices. These includes Azure IoT Device SDK, Azure IoT certified devices, security programs for Azure IoT, and as well as Windows 10 IoT. Now, the IoT services that is provided by the PaaS technology, excuse me. So this IoT suite consists of a bunch of technologies. One of them is Azure IoT Hub, which is basically a managed service that enables bidirectional communications between millions of IoT devices and a solutions at the backend. Azure Time Series Insights, which basically enables you to store, visualize, and query large amount of time series data generated by IoT devices to gain actionable insights. No, I'm not changing my slide at the moment. If you focus on the last point, it has 4 categories. One is device, one is IoT, the other one is data and analytics, and the other one is visualization and integration. So I am currently talking about the IoT. So if you could patiently hear me out, you would know that IoT suite consists of Azure IoT Hub, which I just covered, Azure Time Series Insights. So Azure Time Series Insights enables you to store, visualize, and query large amount of time series data generated by IoT devices to gain actionable insights. Then there is Azure Sphere, which is basically an end-to-end solutions for securing microcontroller power devices. Azure Sphere comprises of 3 parts. One is an Azure Sphere operating system. The other one is an Azure Sphere certified MCUs, microcontroller units, and the third one is Azure Sphere security service brokers. Thus, Azure Sphere allows you to build new devices and connect existing equipments securely using end-to-end security. Yes.
You're not audible.
I'm not. Is this for all?
No, you are audible.
Okay. And ma'am, in that case, kindly check your internet connectivity. Probably there's a drop from your side. Okay.
Please check your end. She's audible. Sukanya is audible.
Thank you. Talking about the IoT suite again, it also consists of Azure IoT Edge. So IoT Edge is built on top of IoT Hub. IoT Edge basically enables you to move parts of your workload to the edge devices and create better experience for your customers. Then there's something called IoT Hub Device Provisioning Service. So Azure IoT Hub Device Provisioning Service is basically a helper service for IoT Hub. The device provisioning service enables customers to provision millions of devices in a secure and scalable manner. Azure Digital Twin is also another service that comes under the IoT suite. Azure Digital Twins basically enables you to model the relationships and interactions between people, spaces, and devices. This ability allows you to create models of a physical environment that you are interested in analyzing. Once the environment has been modeled, you can run predictive algorithms to anticipate the behavior of the entire system. For example, you can optimize the use of available space for an office if the office is modeled through digital twin by replicating the physical space entirely. So digital twin at the end of the day is basically a virtual replica of a physical space. Then IoT suite also consists of Azure Maps, So Azure Maps is a collection of geospatial services that uses fresh mapping data to provide accurate geographic context to web and mobile applications. You can add spatial analytics, mapping services, and mobility services to your app using the APIs. Then the third is within the PaaS technologies, data and analytics services. So for that, there's something called Azure Machine Learning that takes care of the entire data and analytics needs. And the fourth one is visualizations and integration services. So these are various services like Power BI, Azure Logic Apps, Azure Web Apps provided by Microsoft and Azure itself for your dashboarding needs. Okay, so moving on, then we'll talk about Azure IoT Hub. What is Azure IoT Hub? So Azure IoT Hub, as I mentioned briefly previously, it enables secure and reliable communications between your IoT solutions and the devices it manages. IoT Hub provides a cloud-hosted solutions which is the backend of the connected devices. It also allows per device authentication, individual device management, as well as device scale provisioning. So first of all, let's look at some of the definitions. Talking about the IoT Hub, something that comes in mind is telemetry. So what is telemetry? Telemetry is basically the process of recording and transmitting values received by an IoT device. Telemetry is basically an essential functions of an IoT solutions. Provisioning, what is provisioning? The act of provisioning a device to the cloud uniquely identifies the device to the cloud as well. Provisioning also establishes the security protocols for the device and its access rights and privileges. Then there is something called routing. Message routing basically enables you to send messages from your device to cloud services in an automated and scalable as well as reliable manner. You can send either device telemetry message or events, for example, device lifecycle management. Scaling. For cloud solutions, scaling involves the need to ramp up or down the scope of the solution. The ability to scale a solutions up and down gives the developer the flexibility to deploy different kinds of solutions. Service availability. Service availability basically talks about ensuring an agreed level of operational performance, typically called uptime, for the cloud service. Service availability is defined by the service level agreements. Now, IoT Hub enables you to secure your communications. So IoT Hub enables secure communications for your device to send data, providing per device authentications with multiple authentication types. It also scales your solution. IoT Hub allows you to scale to millions of simultaneously connected devices and millions of events per second to support your IoT workloads. Also, there are two considerations when it comes to scaling your solutions. The feature you plan to use and the amount of data you plan to move daily. Azure IoT Hub offers two tiers. One is a basic tier architecture, basic tier pricing, and the other one is the standard tier pricing. To develop a full featured and bidirectional communication capabilities, you should use the standard tier. And the basic tier basically provides a subset of features and is intended for solutions that only needs unidirectional communication from device to the cloud. Both basic and standard tiers offers the same security and authentication features. It also allows you to route device data, which means that IoT Hub enables you to send messages based on automated rules to optimize the data traffic. Then IoT Hub also allows you to send commands to the devices. IoT Hub enables you to send cloud to device messages or cloud to device messages enables you to send commands and notifications to your connected device. So this is where your cloud is sending the necessary actions to your things. Then monitor your IoT Hub also monitors your IoT solution health. So IoT Hub allows tracking of events such as device creations, device communication failures, and device creations, right? Then it also, IoT Hub also helps you to integrate with other devices. You can seamlessly integrate IoT Hub with other Azure services to build an end-to-end solution. Then IoT Hub also manages and configures your devices. Using IoT Hub, you can manage your connected devices at scale. You can also set and query the device status and automatically respond to a change in the state of the device. Then IoT Hub also allows you to create highly available and resilient solutions, which means that your uptime of the solution is pretty high. I mean, basically always. So it allows you to create solutions which are highly available as per specified service level agreements and benefits from the failover capabilities. It also allows you to connect to virtually any device. Using IoT open source device SDK, you can build solutions which runs on connected device and interact with IoT Hub. You can also connect device natively to the IoT Hub using protocols such as MQTT, HTTPS, AMQP, etc., etc. Okay, so these are some of the features when it comes to IoT Hub. Now, how IoT Hub works? So IoT Hub, Azure IoT Hub is the main Azure platform as a service solution that, or platform as a service, platform as a service solution which enables bidirectional communications between IoT devices and the cloud solutions. IoT Hub is the starting point for any IoT solutions when it comes to Azure, and it implements some essential functions that are common to your IoT deployments. These includes networking, compute, storage capabilities, and security. Some of the features of the IoT Hub includes the protocols which are supported by IoT Hub. So IoT Hub allows device to use the protocols, device-side protocols such as MQTT, MQTT over WebSocket, AMQP over WebSocket, and HTTPS. Then there is something called device identity registry. So IoT Hub maintains an identity registry. The identity registry stores information about the devices and modules permitted to connect to the IoT Hub. An identity registry entry for the device or module must exist before the entity can connect to the IoT Hub. A device or module must also authenticate with the IoT Hub based on credentials stored in the identity registry. Also, IoT Hub enables you to perform authentication of the devices. So Azure IoT Hub grants access to endpoints by verifying a token against the shared access policies and identity registry security credentials. You can also use X.509 certificate to authenticate a device with IoT Hub. Supported certificates includes an existing X.509 certificate, CA-signed X.509 certificate, self-generated and self-signed X.509 certificate as well. Then there is something called device twin. So device twin is different from digital twin. Device twin is something that is very much native to just Azure. So device twins are JSON documents that store device state information, including metadata configurations and conditions. Azure IoT Hub maintains a device twin for each devices that you connect to IoT Hub. Device twin also stores device-related information that device and backends can use to synchronize device conditions and configurations. Now, endpoint and IoT Hub exposures. So IoT Hub also exposes your device to particular endpoints. For each device in the identity registry, the IoT hub exposes a set of endpoints, which basically sends device to cloud messages. It also enables to receive cloud to device messages. It initiates file uploads, retrieve and update device twin properties, receive direct method requests. IoT Hub also supports Azure services for provisioning additional custom endpoints such as Azure storage containers, Event Hub, service bus queues, service bus topics. All of these are also supported by Azure IoT Hub. Then device provisioning with Azure IoT Hub. So IoT Hub has something called IoT Hub device provisioning service that allows you to provision your devices. So it basically is a helper service for your IoT Hub. The device provisioning service enables zero touch, just-in-time provisioning to the right IoT hubs, which requires minimal or no human intervention at all, allowing the customer to provide millions of devices in a secure as well as scalable manner. The telemetry functions of the IoT Hub is an essential component. The telemetry function involves recording and transmitting values received by an IoT device. However, IoT Hub is much more than just basic telemetry function. The scaling features of the IoT Hub allows you to ramp up or down the scope of the solution. The ability to scale a solution depends on two considerations: the feature you plan to use and the amount of data you plan to move daily. Once you plan to deploy the services, the device at scale, you just need to manage these devices, right? So the provisioning function of the IoT Hub enables you to manage these devices across the lifecycle of the device. Provisioning also establishes the security protocol for the device, its access rights as well as privileges. The security right can be seen as a part of security function, which manages the per device authentication and access requirements with multiple authentication types. Based on the security functions, the routing function determines the message flow and the recipients of the messages. Finally, you can connect to external devices natively by using the SDK functionality and integrate that with other services using the service integration functionality. As you consider the scenarios outlined before about the solution developer working with multiple sensors in the city, the prototype would actually have to be started with a basic telemetry function, right? So when you are building applications with multiple sensors, let's say a smart city network, then it has to start with telemetry function. But in order to deploy these networks across the city, many more elements are eventually needed beyond the telemetry. These includes the ability to deploy and provision the devices at scale, also implement the device level security, and ensure message level routing. Due to the diversity of the devices in a city, the ability to connect natively using an SDK will expand the user base of the solution. In the absence of the functionality from IoT Hub, the solutions would be hard to deploy beyond just the basic telemetry function, right? So this is, by talking about IoT Hub, this is what we are mentioning, that the compute necessary for IoT even before we can move to the IoT analytics phase. Now, moving on, another service that is essential for us to know in terms of Azure IoT Suite is the Azure IoT Edge service. So Azure IoT Edge is basically a combination of cloud services that are running in the cloud and a runtime that basically runs on your IoT devices. The runtime starts and manages the workflows on the device. The workflow comprises of a set of containers that you link together in a specific order to create the end-to-end scenario. IoT Edge is managed by IoT Hub. The IoT Edge enables you to run workloads on the edge devices, which are deployed using cloud services. The workload is a module deployed using Docker-compatible containers. The module could be artificial intelligence applications or any other Azure third-party services or your business logics. Okay. IoT Edge enables you to react in near real time to local changes because mostly you can implement some functionality at the edge. The device spends less time communicating with the cloud. Hence, the device can react quickly to local changes by processing the data on the device and reducing the latency. Also, when the modules run locally, they can avail the option to use specialized hardwares such as FPGAs or field programmable gate arrays. Then Azure IoT Edge also enables you to manage your edge devices. Azure IoT Edge provides a cloud interface and a runtime module, which enables you to manage remotely and deploy workloads to edge devices through IoT Hub. IoT Edge also enables you to deploy using containers. IoT Edge allows you to use Docker-compatible containers to run your business logics at the edge. Also, another functionality provided by IoT Edge is deploy using secure as well as certified hardwares. So IoT Edge basically enables you to access certified IoT Edge hardwares on Linux or Windows devices that supports container engines. It as an IoT Edge also enables you to distribute AI and analytics workloads to the edge. So IoT Edge allows you to deploy the models that you have built and trained in the cloud and run them on edge devices. IoT Edge also uses the modules to process data locally and responds to any events rapidly. You can also use the Azure IoT Edge capabilities with your existing skill sets. Like if you have developers who are working on C or C Sharp or Java or Node.js or Python, then those developers would be capable of using the IoT Edge, because IoT Edge supports all of these programming capabilities. Also, IoT Edge manages your data to reduce the cost. So remember the edge principles that we were talking about. It processes the data closer to the things, and only insights are sent to the cloud. So Azure IoT Edge device basically captures large amount of data, but typically you only need a small portions of the data to be for further analysis. So if you send all the data to the cloud, then in that case, the user will incur transportations and storage costs. IoT Edge basically reduces the cost by allowing you as the application owner to send only a segment of data as needed. You could also send aggregated data to the cloud, but it really depends on you. Azure IoT Edge enables you to perform that initial analysis and send just whatever is needed to the cloud. Now, sending aggregate, if you choose to send aggregate data, sending aggregate data to the cloud reduces the overall cost of managing the data and transporting the data through reduced bandwidth and storage cost. So this is how IoT Edge enables, Azure IoT Edge enables you to manage the data and reduce the cost. Okay, Then Azure IoT Edge also enables you to operate reliably in offline or intermittent mode. So often IoT Edge device needs to work in an intermittent or offline connectivity to the cloud. This is one of the challenges that we covered while talking about the transmissions of data challenges when it comes to IoT. So IoT Edge devices basically provides management functionality, which automatically synchronizes the latest state of your device once they have reconnected to the cloud to ensure seamless operations. Also, IoT Edge provides security for your edge deployments. So IoT Edge provides security in several ways. Working with the IoT Hub, we can ensure that only the right device can communicate with each other and they have the right set of softwares installed. IoT Edge can also provide added security by integrating with Azure security centers. Also, IoT Edge can make sure of the hardware security modules, if available, to provide strong authenticated connections for confidential computing. Also, Azure IoT Edge ensures privacy of your IoT deployments. So Azure IoT Edge can protect person-related data. Person-related data can be cleansed before it is sent to the cloud. In that way, it provides better privacy protection. Also, by storing data on-premise, you can comply better with security, confidentiality, and privacy regulations. Azure IoT Edge also acts as a gateway. IoT Edge can function as a protocol gateway and thus also provide connectivity and edge analytics to the IoT device that would otherwise not have these capabilities. Also, Azure IoT Edge enables you to connect to any other third-party services which are provided within the Azure itself. Okay, there are some questions on feedbacks forms. Okay, fine. Moving on. So how does IoT Edge work? So talking about the workings of IoT Edge. IoT Edge basically comprises of three components. One is an IoT Edge module. Second is an IoT Edge runtime. And the third is IoT Edge cloud interface. So the IoT Edge modules are basically units of executions which are implemented as Docker compatible containers. IoT Edge modules can run business logics at the edge. IoT Edge module can also run Azure services, any other third-party services, or anything that you have coded for your specific application needs. Modules are basically deployed to IoT Edge devices and execute locally on those devices. You can configure modules to communicate with each other to create a pipeline for data processing. Modules can run offline if needed. IoT Edge runtime runs on each IoT Edge devices and manages the runtime and communications for the modules deployed on each device. IoT Edge runtime ensures that the modules are always running and reports module health to the cloud. The runtime performs several functions such as installing and updating workloads, maintaining the IoT Edge security standards, managing communications between downstream leaf devices as well as IoT Edge devices, managing communications between modules on an IoT Edge device, and managing communications between an IoT Edge device and the cloud. IoT Edge cloud interface enables you to monitor and manage IoT Edge device remotely. If your solutions is running on a diverse set of devices at scale, you can create and configure a workload to run on specific types of devices. You basically then need to deploy the workload to a set of devices of that type. Once the devices are running, you just need to monitor the workloads centrally. IoT Edge Cloud interface also allows you to manage this overall life cycle at scale for a diverse set of devices, which would otherwise, which could be geographically dispersed or scattered. It is challenging also to manage the software lifecycle for millions of IoT devices that are often different and that are of different makes and also models or in diverse locations, right? So workloads are created. So when I say different makes, I hope you get that. Different makes as in different providers are making those different IoT hardwares and softwares, each having their own standards. So workloads are created and configured for a particular type of device, deployed to all of your device, and monitored to catch any misbehaving device. These activities can't be done on a peer device basis, and must be done at scale. Considering the case of deploying complex event processing or machine learning on edge device, if you want to implement machine learning on edge device, then you first train the model in the cloud. After training the model, you need to deploy the trained model to a diverse range of devices, which are often present across geographies. Once deployed, the models will run often offline on the device. You would also need to update the model periodically. By encapsulating the models in a Docker-compatible containers, IoT Edge can manage the end-to-end cycle of deployment for machine learning on IoT. IoT Edge runtime and the cloud interface can monitor the status of the machine learning modules. In the absence of IoT Edge, the developers would basically need to create all the added functionality for just maintaining the module, which is now served by the Azure IoT Edge entirely. Okay. So this was all about the Azure most important services when it comes to the Azure IoT suites, and that specifically deals with Azure Cloud and Edge modules. Now we'll see a little bit of a reference architectures on the Azure side and a few use cases. Before that, I would like to take a minute of pause. And if there are any questions, please feel free to unmute yourself or put it in the chat. Or if you want to discuss anything IoT related or applications related, please feel free to ask. No questions? At a high level, is it?
I think that they have no questions. You can continue. Okay. Yeah.
Okay. At a high level, I hope you're understanding the cloud and the edge capabilities when it comes to Azure. And quick questions from me to you, like on behalf of the organizations, since most of you are from educational organizations, do you have cloud access? Do you have any of the cloud access, be it Azure or AWS? Do you know that AWS has AWS Educate program and Azure has some program related to education, where in you as a part of an organization, I mean, your organizations could apply for access to those clouds?
Sure. If any, yeah.
We haven't yet been using like Azure applications, or like we haven't been connected or participated in that cloud.
Okay. Never mind. But yeah, I mean, it's good to know. It's good to let you know that such programs exist, and if you as a part of the organization choose to go ahead with such programs, feel free to do so. I mean, because you get cloud access with some credits, I believe, and you could explore applications on the cloud, right?
Thank you, ma'am.
Okay, so talking about the reference architecture. Okay, so this is a typical example of an IoT reference architecture. So what's happening here is on the left hand side, you have the devices. Then you have the ingest and provisioning of those, ingesting data and provisioning of those devices. Then you have the hot path, warm path, and cold path of processing. And then on the right hand side, you have the management and business integration part of the services. So what happens here is IoT application can basically be described as things or devices that are sending data to generate insights. This insights generates actions to improve a business or process. An example is an engine, the thing sending temperature data. The data is used to evaluate whether the engine is performing as expected, which is the insights. The insights is used to proactively prioritize the maintenance schedule for the engine, which is again an action further, which is again a further action. The reference architecture basically uses Azure PaaS, platform as a service components. Microsoft recommends using Azure IoT Central, which is a fully managed software as a service solutions. It abstracts the technical choices and lets you focus on your solutions exclusively. The simplicity of utilizing Azure IoT Central comes with a trade-off in being less customizable than a PaaS solution. At a high level, there are two ways to process the telemetry data, the hot path and the cold path. The difference has to do with requirements for latency and the data access. The hot path basically analyzes data in real time as it arrives. In hot path, the telemetry must be processed with a very low latency. The hot path is typically implemented using a stream processing engine. The output may trigger an alert or may be written to a structured format that can be queried using analytical tools. The cold path performs batch processing at longer intervals, hourly or daily. The cold path typically operates over large volumes of data, but the results don't need to be as timely as the hot path. In the cold path, raw telemetry is captured and then fed into a batch process. Right? Then you have an architecture. So this architecture consists of the following components. Some applications, so in this particular architecture, some of the applications may not require every component that I would be talking about generally. But at a high level, this architecture has like IoT devices, then cloud gateway, then device provisioning, then stream processing, machine learning, warm path storage, cold path storage, data transformations, business process integrations, user management, security monitoring, all of these sorts. So I'll still talk about the IoT devices and how does it actually come into this reference architecture scenario. So devices basically can securely register with the cloud and can connect to the cloud to send and receive data. Some devices may be edge devices that performs some kinds of data processing on the device itself or in a field gateway. The recommendations for using this kinds of devices is to use Azure IoT Edge service for edge processing. Now, Cloud Gateway. The Cloud Gateway provides a cloud hub for devices to connect securely to the cloud and send data. It also provides device management capabilities, including command and control of those devices. For the Cloud Gateway, the recommendation is to use Azure IoT Hub. We talked about Azure IoT Hub and what it does at length in the previous slides, so won't be talking about that any further.
Ma'am, one question.
Yeah.
Ma'am, wanted to know like whether Edge can control a certain machine in cases of emergency without sending the data to the cloud or without consulting consulting with the cloud. So can it does the Edge has that control over the devices so that it can simply control or give a command to the device in cases of emergency without consultation with the cloud?
Yes. In simple words, it can, because your edge is extending your cloud capabilities, and edge is mostly used for inferencing. So until and unless there are some significant changes to your current training process, model training process, or significant addition of data to your current model, your edge is capable of inferencing right there and trigger any further actions immediately.
Thank you.
Okay. Now talking about device provisioning. So we covered IoT devices, we covered Cloud Gateway. Now talking about device provisioning. So for registering and connecting large sets of devices, the recommendation is to use IoT Hub device provisioning service. Device provisioning service lets you assign and register device to specific Azure IoT Hub endpoint at scale. Next is stream processing. On somewhere in the middle you see it. Stream processing analyzes large streams of data records and evaluates the rules for those streams. For stream processing, the recommendation is to use Azure Stream Analytics, which is another service provided by Azure. Stream Analytics can execute complex analysis at scale using time windowing function, stream aggregation, and external data source joins. Another option is to use Apache Spark on Azure Databricks. Right? Okay. Then there are machine learning capabilities, which allows predictive algorithms to be executed over historical telemetry data, which further enables scenarios such as predictive maintenance. For machine learning, the recommendation is to use Azure Machine Learning Services. When you have warm path storage, so warm path storage basically holds data that must be available immediately from device for reporting and visualizations. For warm path storage, the recommendation is to use Cosmos DB. Cosmos DB is a globally distributed multi-model database. Cold path storage holds data that is kept longer term and is used for batch processing. For cold path storage, the recommendation is to use Azure Blob Storage. The Azure Blob Storage is another service, is basically the storage service provided by Azure. Data can be archived in blob storage indefinitely at very low cost and is easily accessible for batch processing. Data transformation basically manipulates or aggregates the telemetry stream. Examples includes protocol transformations such as converting binary data to JSON or combining any other data points. If the data must be transformed before reaching IoT Hub, the recommendation is to use Protocol Gateway, which is not shown in this reference architecture. Otherwise, the data can be transformed after it reaches the IoT Hub. In that case, the recommendations would be to use Azure Functions, which has built-in integration with IoT Hub, Cosmos DB, and Blob Storage. Then on the right-hand side, you have the user management and the business process integration. The business process integration basically performs actions based on insights from the device data. This cloud includes storing informal messages, raising alarms, sending emails or SMS messages, or integrating with CRM. The recommendation is to use Azure Logic Apps for business process integrations. User management. User management restricts which users or groups can perform actions on devices, such as upgrading firmware. It also defines capabilities for users in applications. The recommendations for user management is to use Azure Active Directory to authenticate and authorize users. For security monitoring, Azure Security Center for IoT is an Azure service that provides end-to-end security solutions for IoT workloads and simplifies their protections by delivering unified visibility and control, adaptive threat preventions, as well as intelligent threat detections and response across workloads from leaf devices through edge as well as through the cloud. So this at a high level was talking about various Azure services, and this gives you a high level so others participants, you're requested to go on mute if you don't have any questions. Anyway, so this reference architecture is basically talking about a reference point of architecture wherein it talks about various services that you can use to build an entire end-to-end IoT application, right? Next, we'll see another very specific architecture, which is Azure IoT Data and Analytics. So this deals with construction equipment. So here you have the construction data going through a traffic manager, through a load balancer to this inbound server, then the database server. And here you have the sensor data going through IoT Hub, blob storage, stream analytics, SQLDB, web app. So in brief, I'll be talking about this architecture now. So this example scenario is relevant to organizations who are building solutions that integrate data from many IoT devices into a comprehensive data analytics architecture to improve and automate decision making. Potential applications include construction, mining, manufacturing, or other industry solutions involving large volumes of data from many IoT-based data inputs. In this scenario, a construction equipment manufacturer builds vehicles, also meters and drones that uses IoT and GPS technologies to emit telemetry data. The company basically, this is a hypothetical situation in that the company basically wants to modernize their data architecture to better monitor operating conditions and equipment health. Replacing the company's legacy solutions using on-premise infrastructure would be both time-intensive as well as labor-intensive and would not be able to scale sufficiently to handle the anticipated data volume. The company wants to build a cloud-based smart construction solutions. It should gather a comprehensive set of devices for our construction sites and automate the operations and maintenance of the various elements of the sites. The company's goal basically includes integrating and analyzing all construction site equipment and data to minimize equipment downtime and reduce theft, remotely and automatically control construction equipment to mitigate the effects of a labor shortage, ultimately requiring fewer workers and enabling lower skilled workers to succeed. Third goal is to minimize the operation cost and labor requirements for supporting infrastructure while increasing productivity and safety. The fourth goal is to easily scale the infrastructure to support increases in telemetry data. The fifth goal is to comply with all the relevant legal requirements by provisioning resources in country without compromising system availability. Also, the last goal is using open source softwares to maximize the investment in workers' current scale. So using managed Azure services such as IoT Hub and HT Insights, it will basically allow the customers to rapidly build and deploy a comprehensive solutions with a lower operation cost. If you have additional data analytics needs, you should review the list of available fully managed data analytics service in Azure. So go to Microsoft documentations, you'll get the list of services that Azure has. So in that case, you can read what each of the services does, and you can use it as per your need in various applications. Now, as I described, this use case and this architecture could also be relevant for other use cases such as construction, mining, or equipment manufacturing scenarios. Also, large-scale collections of device data in any applications that deals with large-scale collections of device data for storage and analysis, and also anything that deals with ingestions and analysis of large data sets. The data flow in this particular architecture is happening as follows. So you have construction equipment that collects sensor data and sends the construction results data at regular intervals to load balanced web servers hosted on a cluster of Azure virtual machines. The custom web services ingest the construction results data and store it in Apache Cassandra cluster, which is also running on Azure virtual machine. Apache Cassandra database is a NoSQL database, and it's storing all the data there. Another data set is gathered by IoT sensors on various construction equipments and sent to IoT Hub. Now, raw data is sent directly from the IoT Hub to Azure Blob Storage and is immediately available for viewing and as well as analysis. Now, the data collected by the IoT Hub is also processed in near real time by Azure Stream Analytics jobs and are stored in an Azure SQL database. The Smart Construction Cloud web application is available to analysts and end users to view and analyze sensor data and imagery. Batch jobs are initiated on demand by users of the web applications. The batch job runs in Apache Spark on HT Insights and analyze new data stored in Cassandra clusters. Components of these components used in this architecture are IoT Hub, which acts as a central message hub for secure bidirectional communications with per device identity between the cloud platform and the construction equipments and other site elements. IoT Hub can rapidly collect data for each device for ingestions into the data analytics pipeline. Azure Stream Analytics. Azure Stream Analytics is basically an event processing engine that can analyze high volumes of data streaming from devices and other data sources. It also supports extracting information from data streams to identify patterns and relationships. In this scenario, Stream Analytics basically ingests and analyzes data from IoT devices and stores the results in Azure SQL database. Azure SQL database, what it does, it contains the results of analyzed data from IoT devices and meters, which can be viewed by analysts and users via Azure-based web application. Then blob storage. So blob storage basically stores image data gathered from the IoT Hub devices. The image data can be viewed via the web application. Then traffic manager. So the traffic manager controls the distributions of user traffic for service endpoints in different Azure regions. Load balancer. So load balancer distributes submissions from construction equipment devices across the VM-based web services to provide high availability. Then you have Azure Virtual Machines, which hosts the web services that receives and ingests the construction results into the Apache Cassandra database. Then there is something called Apache Cassandra, which is a distributed NoSQL database used to store construction data for later processing by Apache Spark. Excuse me. Then there's something called web apps, which hosts the end user web applications, which can be used to query and view sources data as well as images. And user can also initiate batch jobs in Apache Spark via the applications. Then Apache Spark or HD Insights. So Apache Spark on HD Insights supports in-memory processing to boost the performance of big data analytic applications. In this particular scenario, Spark is used to run complex algorithms over the data stored in Apache Cassandra. Now, there could be utilizations of some other alternative services, which is beyond the scope of this session right now. So I won't be going into those. Okay. Any questions on this architecture so far? Anything? All right, moving on. So another application is predictive maintenance with IoT. This is a very famous application and is utilized for any XYZ manufacturing units. So IoT Edge brings data processing and storage close to the data source, which further enables fast, consistent responses with reduced dependency on cloud connectivity and resources. Edge computing can incorporate artificial intelligence and machine learning models to create intelligent edge devices and networks, which can further integrate with the cloud for further processing as well as security. In this particular application, this particular architecture was a collaboration between Microsoft Commercial Software Engineering, which is a CSE team, and a major railway company to create an intelligent cloud and edge train maintenance and safety solution. The railway company wants to improve the railroad safety and efficiency by proactively identifying defective components, predictively scheduling maintenance and repair, and continuously improving their findings and predictions. The pilot project for the ML on Edge solutions is a train wheel health analysis system. Over 4,000 trackside detectors continuously monitor and stream the wheel data from all the company's train. The detector measures heat and force of equipment on the tracks, listens for invisible wheel bearing defects or wheel cracks, and identifying missing or misplaced parts. The ML on Edge system processes and acts on this continuous streaming detected data in real time, in near real time actually, to identify at-risk equipments and also determine the repair urgency, generates alerts, and sends data to Azure Cloud for storage. The IoT Edge module runs on server class hardware in trackside bungalows, allowing for future parallel deployment of other workloads. Bringing machine learning and business logic closer to the data sources, it lets device react faster to local changes and critical events. Devices can operate reliably offline or when connectivity is limited. The edge network basically can determine which data needs to be sent to the cloud and prioritize urgent and important data first. The wheel health analysis system provides early identifications of potential equipment failure, thus helping prevent catastrophic failures that could lead to train derailment. The company can also use stored data to spot trends and inform prescriptive maintenance and overhaul schedules. Now, this use case demands 99.999% uptime, which means that there is no chance that this solution can go offline. It needs to be always alert and keep monitoring 24 hours a day, right? So in this architecture, on the very left hand side, you see a image file server, a network analysis server in a bungalow, which serves the processed and categorized train wheel images. 3 pictures of each wheel creates a stitched image. So when I say bungalow, it means the trackside railway stations that you get in between. When you travel long distance over train, you get to see those railway bungalows, right? So the servers are kept in those bungalows that continuously keeps on imbibing data and performs the necessary actions. So 3 pictures of each wheel creates a stitched image. The polling module basically alerts the edge devices that new images are available for processing. A third-party ML model processes the images and identifies the wheel areas that needs more inspection. The alert handler uploads all the images into Azure Blob Storage, starting with images that have the potential defects, and returns the image blob URIs, or the uniform resource identifiers. The IoT Edge Hub associates the image URIs with image metadata and uploads the metadata and alerts to Azure IoT Hub. IoT Hub sends the metadata via Event Hub and Azure Functions to an Azure Cosmos DB database. The Cosmos DB database basically holds the image metadata and points to the locations of images in Azure Blob Storage. Now the components used here in this architecture is the deployed solution requires an Azure subscription, of course, that's the very basic need, with permission to add services principals and the ability to create Azure resources. Azure IoT Edge is made up of 3 components: IoT Edge modules, IoT Edge runtime, and the Azure IoT Hub interface, which enables secure bidirectional communications. Also, IoT Edge ML supports Azure Machine Learning, a third-party, and third-party ML modules for custom code. The current solutions uses a third-party open source ML called Cogniac to score train wheel data and recognize potential defects. The ML software uses historical samples of high and low confidence failure images to retain its ML model. Azure Blob Storage is Microsoft's object storage solutions for the cloud. Blob storage is optimized for storing massive amount of unstructured data, like the image data in this example. Azure Cosmos DB is a fully managed NoSQL database service with low response times and high availability and scalability. Azure Pipeline Workload builds, tests, and deploys and archives the IoT Edge solutions through built-in Azure IoT Edge tasks. Okay, so these are examples of, these are the components used for this particular set of architecture, which basically helps you build this entire applications end to end. Now, any questions here so far on the Azure architectures and the use cases that we covered? Anything? Any questions? All right.
Madam,
yeah.
In case of Edge, how do things can be done offline?
How things can be done?
Offline. Ma'am, you mentioned that something can be carried out offline if you are employing Edge.
Oh yes. So in that case, as I mentioned, the cloud capabilities are so Edge. For Azure IoT Edge, it provides a runtime that basically replicates the some of the capabilities, some of the necessary capabilities of cloud on the Edge side. Now, Edge is closer to the IoT device. Now, internet connectivity is required only when there has to be to and fro communications between cloud and the Edge, right? But otherwise, if you deploy an entirely trained model on the edge side and use it for inferencing, then in that case, your edge is capable of performing on its own without any network connectivity, and that's how offline mode is enabled. So, and then further, when you need to actually transfer those data online, then when a connectivity is established, then in that case, the edge sends all the processed information to the cloud. Did that make sense to you?
Yes, ma'am. Thank you.
Yeah, thank you. Okay. Any further questions? Okay, so moving on, we have Azure AWS IoT services for industrial applications. So here are the is a kind of map for the services that are present on the AWS side. Here you have the industrial equipments, then you have the data servers and historian databases and free RTOS. Azure SiteWise and Azure IoT AWS SiteWise, IoT SiteWise, Edge, and AWS IoT Greengrass are for edge computations. Then you have AWS IoT SiteWise in general, which are used for data management. Then you have device connectivity and control. So AWS IoT Things Graph, AWS IoT Core, AWS IoT Device Management, and AWS IoT Device Defender. All of these are used for device connectivity and control. And then you have AWS IoT Events and AWS IoT Analytics, so which are used for analytics and event detection. So this is a reference architecture. So at the device layer, yeah, so at the very bottom we have the device software, then we have the control services, then we have the data services. So at the device software layer, we have AWS IoT Greengrass. So AWS IoT Greengrass basically extends IoT to edge devices so that they can act locally on the data they generate and use the cloud for management, analytics, and durable storage. With AWS IoT Greengrass, connected device can run AWS Lambda functions, Docker containers, as well as. Okay. So let me put it this way. So when it comes to AWS IoT Greengrass, connected device can run both AWS Lambda functions, which are serverless solutions, as well as Docker containers, which are containerized solutions, or both. So Greengrass is capable of running both of these together, and also executes predictions based on machine learning models, keep device data in sync, and communicate with other devices securely, even when they are not connected to the internet. So this is a capability provided by Azure. This is a capability provided by AWS. AWS IoT Greengrass, much like your Azure IoT Edge. So all of these at the software layer itself, this managed cloud service provider takes care of the intermittent or offline connectivity. Okay. Then again at the device software layer, we have the AWS IoT Device Tester. So AWS IoT Device Tester for free RTOS and AWS IoT Greengrass is basically a test automation tool for microcontrollers. AWS IoT Device Tester tests your device to determine if it will run free RTOS or with AWS IoT Greengrass and interoperate with AWS IoT services. AWS IoT Device SDK, AWS IoT Device and Mobile SDKs basically helps you efficiently connect your device to AWS IoT. Just a minute. Yeah, I'll just go. Okay, so AWS IoT device and mobile SDKs includes open source libraries, developer guides with samples, and porting guides so that you can build innovative IoT applications and product solutions in using the choice of your hardware platforms. FreeRTOS is an open source real-time operating system for microcontrollers that lets you include small low power edge devices in your IoT solutions. FreeRTOS includes a kernel and a growing set of software libraries that supports many applications. FreeRTOS systems can securely connect your small low power devices to AWS IoT to support more powerful edge devices running AWS IoT Greengrass. Make sense? Next, on top of this, we have the control services. So control service basically manages the devices in your IoT solutions. So for that, we have IoT Core, which is a managed cloud service that enables connected device to securely interact with cloud applications and other devices. AWS IoT Core can support many devices and messages. It can process and route those messages to AWS IoT endpoints and other IoT devices. With AWS IoT Core, your applications can interact with all of your devices even when they aren't connected. AWS IoT Device Management Services helps you track, monitor, and manage plethora of connected devices that makes up your device fleet. AWS IoT Device Management Services helps you ensure that your IoT device work properly and securely after they have been deployed. They also provide secure tunneling to access your devices, monitor their health, detect and remotely troubleshoot problems, as well as services to manage device softwares and firmware updates. AWS IoT Device Defender. AWS IoT Device Defender helps you to secure your fleet of IoT device. Also, it continuously helps you audit your IoT configuration to make sure that they aren't deviating from the security best practices. AWS IoT Device Defender sends an alert when it detects any gaps in your IoT configuration that might create a security risk, such as identity certificates being shared across multiple devices or device revoked with identity certificate trying to connect with AWS IoT Core. AWS IoT Things Graph is another service that lets you visually connect different devices and web services to build IoT applications. AWS IoT Things Graph provides a visual drag and drop interface for connecting and coordinating interactions between devices and web services so that you can build IoT applications efficiently. On top of that, you have the AWS Data Services. So this is where you analyze the data from device in your IoT solutions and take appropriate actions by using the following AWS IoT services, like AWS IoT Analytics, AWS IoT SiteWise, and AWS IoT Events. So AWS IoT Analytics lets you efficiently run and operationalize sophisticated analytics on massive volume of unstructured IoT data. AWS IoT Analytics also automates each different step that is required to analyze data from various IoT sensors or devices. It also lets you filter, transform, and enrich the IoT data before storing it in a time series data store for analysis. You can analyze any data by running one-time or scheduled queries using the built-in SQL query engine or machine learning. Then there's something called AWS IoT SiteWise, which collects, stores, organizes, and monitors the data that is passed on from industrial equipment by MQTT messages. MQTT is a protocol, again, much like your Bluetooth protocol, your LoRaWAN protocol, your TCP protocol, right? Which, equipments by MQTT messages or APIs at scale by providing software that runs on the gateway in your facilities. The gateway securely connects to you on-premise to your on-premise data servers and automates the process of collecting and organizing the data and sending it back to the AWS cloud. Last but not least, the AWS IoT events basically detects and responds to events from IoT sensors and applications. Events are patterns of data that identify more complicated circumstances than expected, such as motion detectors using movement signals to activate lights and security cameras. AWS IoT events also continuously monitors data from multiple IoT sensors and applications and integrates those with other devices such as AWS IoT Core, IoT Sitewise, DynamoDB, and others to enable early detections and unique insights. Right? So this at a high level are various AWS, basically this is an AWS IoT suite that basically helps you create IoT applications on AWS. Right? So any questions here so far? If not, I'll just move on to the next slide. I'll just take 30 seconds of pause and then talk to you about this architecture. Okay, so here this is an applications of connected home where you're performing machine learning at the edge. So follow the numbers here that starts the architecture, and this entire architecture flows through the home, connected home application, right? So what's happening in this connected home application is, first of all, look at the camera sensor on the left hand side. So you have an IoT enabled video camera which is running AWS IoT Greengrass, which publishes the training data to the AWS IoT core. Then you see number 2, it has an IoT rule that is listening for camera data that forwards the messages to Amazon Kinesis Data Firehouse for storage in Amazon S3. Then you have Amazon SageMaker so follow the third path. So here Amazon from S3 to Amazon SageMaker. So Amazon SageMaker is basically used to train, optimize, and build machine learning models that can use less than 1/10 of the memory footprint found in resource-constrained devices like cameras. Then you have something called, follow the fourth line. Post the Amazon SageMaker is training the machine learning model. The Amazon's on the fourth step, it basically outputs the trained model to another Amazon S3 bucket. Amazon S3 is the default storage of when it comes to AWS. So it's pushing it to Amazon S3 for delivery to the IoT video camera. Then on the fifth hand side, you have the AWS IoT Greengrass, which are cloud services, which is used to orchestrate the deployments of software to target IoT video camera, including trained models and application logic such as AWS Lambda functions on Docker containers. The sixth one on the left hand side, you see is a Lambda function that runs locally on the IoT video camera, which performs inferencing using the latest version of the model trained. So you train the model on the cloud on the right hand side using SageMaker on AWS cloud. And then you just push the trained model, the inference piece of the code, to the Lambda function. And that piece of code is particularly running on the edge device, which is the camera sensor, and performing all the inferences as required. Inference is nothing but just predicting as required, right? So when it comes to machine learning, you have model building phase, you have model training phase, wherein you train your model and then post your model training, evaluate, and then you use the trained model for inferencing. Right, so this is what is happening. Then follow the 7th part. So in this, the homeowner can use mobile applications to view cameras video streams via Amazon Kinesis video streams. Right? So in this, so your camera sends the real-time feed to the Amazon Kinesis video stream, and then from there, you as a user can get the data output to your mobile application. Got it? How this application is working, how your connected home application is working. So this is applicable for any XYZ applications, any XYZ things at your home that is IoT enabled, and you can use this reference architecture, maybe tweak it a bit here and there, change it basis on your requirement, and you can develop any XYZ connected applications. Got it? Okay. Then moving on. You have the AWS industrial. Next part is the predictive maintenance, ML model. So predictive maintenance, one set of architecture we saw on the Azure side. Now we'll see here on the AWS side. So here what it's doing is, it's creating a predictive maintenance machine learning model using AWS IoT Sitewise and AWS IoT Analytics. So AWS IoT Sitewise basically collects, organizes, and stores data in the cloud, making it available for data scientists to train ML models with clean, contextual, and structured data sets. Again, here in this architecture, follow the numberings of the path. So at the very first layer where you have 1 written, you configure the AWS IoT Sitewise connector on AWS IoT Greengrass to connect and collect data from factory machines using OPC UA. All right. Then on the second part, then after you connect to the AWS IoT Site connector, on the left hand side you have the factory, which is the edge. Then on the right hand side you go to the AWS cloud, right? So here, the second part is using AWS IoT Sitewise to model and create assets that represents on-premise device equipments and processes and ingest the data on AWS. Okay. Then the third part from there is you create a custom web portal using Sitewise monitor functionality to visualize factory data and industrial performance metrics in near real time, accessible and credential setups in AWS single sign-on. The fourth part is using an IoT rules engine to get into an AWS IoT analytics for additional insights on your data. Then the fifth part here on the left-hand side is for other industrial data you want to process, you can use AWS IoT Greengrass Stream Manager and publish that to the AWS IoT core, right? Then follow the sixth part. You build a Docker image that is added to an Amazon ECR, Amazon Elastic Container Registry that basically manages Docker images. Okay. Then follow the seventh part. In the seventh part, you have an AWS IoT Analytics, which creates a container data set from the AWS IoT Sitewise data store and link it to the Docker container. Then the eighth path is basically you perform analytics. So from AWS IoT Analytics, you create a new Jupyter notebook for the data set created from the AWS Sitewise, which further would be used, this data set would be used for building the predictive maintenance ML model. And on the ninth part, you have Amazon QuickSight, which is a visualization tool, which is a visualization software provided by AWS, which helps you visualize your analysis using this QuickSight service on the AWS IoT Analytics data source. Got it? So this is another applications using this is another end-to-end IoT applications using both edge and cloud, that could be that is used to build something on a factory floor. Okay. Another architecture, since we have time, is predictive quality reference architecture. So what's happening in this is you are required to create a computer vision predictive quality machine learning model using Amazon SageMaker with AWS IoT Core, AWS IoT SiteWise, AWS IoT Greengrass, and AWS Lake Formation. So all of these are AWS services. So again, on the left-hand side, you have the factory, and on the right-hand side, you have the cloud. So on the factory side, factory is basically acting as your edge, and cloud is your AWS cloud, right? So again, follow the numbered routes. So number 1 basically denotes, so you're configuring you have the factory stations wherein you're configuring an AWS IoT Greengrass to communicate with industrial equipment to capture data and video on the factory floor, right? So once you capture that video and data, come to second, the arrow that is marked as number 2. So in this, you configure the AWS IoT SiteWise connector on AWS IoT Greengrass to connect and collect data from factory machines using OPC UA. Now come to the third part. Once you have put in the data in AWS IoT SiteWise, you use AWS IoT SiteWise to model assets that represents on-premise devices, equipments, and processes, and ingests historian data into AWS. Then come to the fourth part, which is below the second one, right? So here in this, you use AWS IoT Greengrass to exchange messages with AWS IoT Core and send processed images to Amazon S3 on your AWS Lake Formation, right? And then here, then come to the fifth part, wherein you configure rules within AWS IoT Core to trigger events and send data to AWS IoT Events and AWS IoT Analytics. So see, from AWS IoT Core here, from AWS IoT Core here, 2 arrows are going, one to AWS IoT Events and one to AWS IoT Analytics. Then what happens is the sixth part. So here from the video uploader, you put it to an Amazon Lake Formation, right? AWS IoT Analytics is also giving in data to the Amazon Lake Formations, and Amazon Lake Formation is further pushing the data to the AWS SageMaker. So again, in SageMaker, what's happening is you build a predictive quality machine learning model using SageMaker based on the images stored in the AWS Lake Formation. Then on the seventh part, what's happening is the ML inferencing. So you deploy your trained ML model into your AWS IoT Greengrass Edge Gateway. Right? So this is when inferencing is happening. Now come back to here. You have IoT events. From here you push it to an Amazon simple notification service. Right? So simple notification service is basically used to notify the operations engineer. So this is how the operations engineer are getting notified regarding any triggered events, right? And last, the ninth part is basically taking in data from the AWS IoT SiteWise and also creating a dashboard, which is basically a visualizations of the factory data and other industrial KPIs in near real time, and then also feeding into the operation managers. And the 10th one here, AWS IoT Analytics, it's again passing it through, post your certain analytics, it's passing in through QuickSight, which is again the dashboard or the visualization service provided by AWS. And then that dashboard is also again fed to the operations manager present on the factory floor. So this is again an end-to-end scenario. This last architecture is a little complex, but then again, this is an end-to-end IoT scenario that is happening on any factory floor, and all the operations manager could keep a track of what's happening with various levels of analytics, and therefore connectivity or the Internet of Things creating further and the final values to it. So when I say final values, you remember at the beginning, I talked about why IoT and what is the necessity of connecting everything over the internet, basically to generate value. And now in a factory floor, it is not always possible to keep track of everything at a human level. A lot of things are happening, and as and when for huge factories like your power generation factory or anything of that sort, it's impossible to keep a track and audit every unit, right? Even though it was done, but still, of course, something or the other was always left out. So in that case, connectivity and analysis at the end of the day is further generating value to it. So with this, I conclude my session. I'll stop sharing. If you have any questions, feel free to ask, or else I hand it over to ma'am. Ma'am, are you there on the call?
Yes, ma'am. The participants have any questions? I don't think so.
Yep.
Okay.
So
thank you, ma'am.
Yeah.
I thank you from the bottom of our hearts for taking time to be our teacher today. We look forward to our next interaction very soon. And thank you all participants for listening to this enlightening PPT and lecture. We will break for lunch and we will meet again in half an hour. Okay.
Thank you all for hearing me out and letting me speak on IoT, and see you soon. Thank you all. Bye-bye.
Bye, ma'am. I hope you have filled the second session's attendance forms, and we will meet again after lunch. And there will be a small, as sir told you in the morning, a very small session by the industry person. And after that, there will be a test. Thank you. Pranav sir, am I audible?
Yes, Queen, you are audible.
Yes, audible, madam.
Participants, our guest speaker has joined. We will start in few minutes. Pranav sir. Sir.
Hi, good afternoon.
Good afternoon, sir. We will start in 2 minutes.
Sure, ma'am. Am I audible and am I visible?
Yes, sir. Yes, sir.
Okay, great.
We will begin. Okay.
Sure.
Good afternoon, participants. So this is our last session of today's FDP. We have the privilege of having Sir Shri Pranav Pathak sir with us. He is currently product manager at Wipro Technologies. He has completed engineering in computer science in the year 2004 from UIT-RGPV. Post-engineering, he went for higher studies and completed his MBA from Management Development Institute, Gurgaon, with information systems as his domain of specialization. He has a total of 14 years of professional experience of working with organizations like Bosch, KPMG, and Wipro Technologies. He has been extensively involved with customers across industrial domains and geographies, and solving their business problems by utilizing transformative new age technologies such as IoT and blockchain. He is the recipient of Aegis Graham Bell Award in the category of Technology Innovation organized by the Ministry of Micro, Small and Medium Enterprises from Government of India for the year 2020. Sir, we welcome you and we are very thankful that you are here to enhance our FDP with your presence and share your knowledge. You have been made the co-host and you can start sharing your slides if you want to.
Thank you so much. Just give me a minute. Let me start with sharing my slides. Hi, do you see my screen now?
Yes, it's visible.
Okay, great. Thanks. So, Hi, everyone. First and foremost, thanks for giving me the opportunity to share my experience in this session. As it was stated during my introduction, I did my engineering from SoIT-RGPV in computer science in the year 2004. In fact, I was a part of the batch, that was among the first few batches that passed out from RGPV campus situated in Lal Ghati. And I know that many of the esteemed faculty members who are listening to me today have been my teachers and mentors during my graduation days. It is indeed a very humbling experience to talk to the same faculty members from the other side of the table now. So thanks again, and let me start. In the last 14 years of my professional life, I have worked on multiple technologies such as ERP suites like SAP, Oracle, etc. I have seen the evolution and the adoption of cloud frameworks and services. However, most of these technologies and areas of innovation were heavily focused on enterprise processes, right? So, for example, it did not really matter what type of ERP system our bank is using, or what kind of cloud service does my email service provider use in the backend, as long as my task was being done, right? Now, when we compare that to the way latest technology innovations like blockchain and IoT are impacting our lives, there is a huge difference. And the difference is that these technologies have actually moved out of the offices of CIOs and CEOs and have started impacting our day-to-day lives. These technologies have already started to radically transform the way we conduct business and the way we live our lives. My prime responsibility has been to work with customers, identify their pain points, and try and find the best, most cost-effective and reliable solution for them. Get the solutions built with the help of our technology experts, and then deploy the solution for our customers in their premises or in their business areas. I have seen the recordings of other sessions that were conducted before me in this particular event, and I know the kind of detailed technology perspective that these sessions have given. So I will try to rather focus more on the business and enterprise needs of organizations today, and how these technologies like IoT and blockchain help organizations address these needs. Okay, so this slide is an agenda of the session today. We will take a historical perspective and with an example try to understand how value creation, storage, and transfer has been happening in the different monetary systems across the world. And how does blockchain fulfill the requirement of a stable, secure mode of storage of value and transfer of value across the globe? We will go into the details of what each component of a blockchain network is, how does the network really work, and how does such a high-stake global network take care of itself without any external intervention. We will then talk about the distributed ledger technology platforms that exist and why organizations have started to adopt them, what kind of problems these technology platforms are solving for them. We will then talk about enterprises, how they are adopting IoT and blockchain in a big way, and what are the problems and integration of IoT and blockchain is helping enterprises to resolve. And then finally, I will talk about a very specific use case that is, focused on the real-time temperature tracking of COVID vaccines, right? I will go into the details of how a combination of IoT and blockchain, has been required, or rather has been, what is the benefit of blockchain and IoT coming together, and why these two technologies should not really be looked in isolation towards the end of my presentation. I will request the audience to please feel free to interrupt me in between if there are any questions, though we have a Q&A session towards the end, but then please feel free to interrupt me because the objective of this session is to make sure that we all can share our knowledge, right? Okay, so this is the first section. The slide that you see on your screen, just give me a minute, let me. Okay, the slide that you see on your screen talks about an island called the Yap Island. And give me a second. How can I hide this? I think the entire screen is not visible, right?
Yeah, screen is visible, Pranav.
Achha, the entire screen. Okay. So for me, because I'm able to see the controls at the top of Zoom, so that's why I thought it's not visible. Anyways, okay. So this slide talks about a very primitive but effective monetary system developed by inhabitants of an island in the Pacific Ocean called the Yap Island, right? This is how their monetary system used to work. the inhabitants would go to another island that was about 400 kilometers away on these small boats that you see on your screen, carve out limestone discs that weighed about 200 kilograms. And when these discs were brought back to the island, they were treated as money. Right now, the idea here was that the creation of money was not something which the entire population could do. There was just a certain set of people who had these resources to create these discs and take it back to their island. That is how the banking system today works as well. Right now, this system worked well for them. These stones were huge, which made it very difficult for them to transfer it from one person to the next. The inhabitants soon realized that there was really no need to do a physical transfer of the stone, right? Because transferring it from one person to the next to, let's say, buy a specific type of product was very difficult, right? So they realized that instead of transferring the stone money, they can develop a new system, right? And what they did was they created a system where a group of trusted adults on the island would keep a record of all the transactions happening on the island. This made their lives very easy, because now there was no need to really, there was no need for a centralized organization to run this monetary system. All the transaction details were maintained in consensus by multiple trusted individuals. So there was no way to go back and change the historical transaction itself. Even if one of the island elders tried to record, because everyone else had agreed to reach a consensus for a specific change, and only when everybody was in consensus this change was made, right? So this was error proof as well. Now, there were accidents. These stones would at times go into the seabed, because the boat would sink and stuff like that. So there was really no need to actually physically own these stones as well. So somebody knew that, okay, on the seabed there is this specific stone lying, and who's the owner of this particular stone, right? So for the first time in human history, people were able to utilize the power of crowdsourcing. They transformed money from a physical asset to a cognitive asset, where everybody was keeping a record of the transaction in their memory, and there was really no need to transfer these stones or transfer the money to the other person to buy stuff. And of course, this system was error-free, transactions were immutable, and there was no central body controlling it as well. So this was an entirely decentralized, distributed system, right? So this is a very primitive way of how a specific island was, developing a monetary system around 580s. Now, moving on to the next slide. Okay. So let's fast forward to a few days from 580 years, which the monetary system of Yap Islanders had. They were recording all transactions. All transactions were on a shared ledger, so everybody had a copy of this ledger. Expensive resources were used to create value or used to create the stone, so not everybody can go and create money. These transactions were immutable, because there were a group of people who had a list of all these transactions, so we cannot really go ahead and change something in the past. These were transparent, these were distributed, these were decentralized, and these were consensus driven. So these were some of the salient properties of the monetary system which Yap Islanders had developed. Towards the end of the session, I will draw a parallel between what these guys have done and what blockchain systems of today are doing, and why are they relevant to IoT technology, right? So we will revisit this slide again. Moving on to the next slide. This is what a distributed ledger looks like, right? So essentially in human history, one of the most critical aspects has been, and which has been many a times overlooked, is the aspect about record keeping, right? Records enable the growth of trade and commerce and proliferation of ideas across the globe. It evolved from keeping records in clay tablets to paper to Excel file, and finally to double entry bookkeeping, and then to distributed ledger. Now, what a distributed ledger essentially is and why it is important today is because when we talk about transactions, it is not just one or two organizations who are conducting transaction and storing value or exchanging value between themselves. When we talk about business transactions of today, it is multiple organizations or multiple enterprises which are a part of these transactions, right? So it's very important to have a distributed ledger system which is consensus driven. So everybody agrees to a transaction and there is a mutual consensus of a data entry. There are multiple participants, which will make it stronger and error proof. There is disintermediation, which means that there is no central intermediary involved, so you don't really have to trust one organization, because trusting one organization creates a problem of single point of failure, right? So if that organization goes down, there's nothing that you can do. These systems should be flexible and secure. They should be tamper proof, and they should be able to store value, right? So value can be in any form. It can be monetary value. It can be value in the form of, let's say, a IP document. I own the intellectual property, and if I have to transfer it to someone else, I today have to depend on a centralized body. And if that centralized body goes down, then there is no way that this IP management can work well. Whereas in a distributed ledger system, there is a group of organizations or group of participants who are maintaining this information and who are facilitating the transfer of this information, right? So that's the whole concept behind a distributed ledger, right? Now, moving on to the more interesting part, blockchain is a distributed ledger in action across the globe. Now, the key benefit or the biggest advantage that blockchain, or the uniqueness with blockchain comes with, is it decentralizes trust, right? So till a few decades back, when internet was evolving, internet came into existence in order to decentralize information, right? So what that means is that, let's say New York Times is being published in New York, and if I have to read that particular newspaper setting in Bangalore, I don't really need to go in and acquire a physical copy of that paper. I can just read a scanned copy of that paper which has been scanned by somebody in New York and sent to me on email, or I can visit the website of the New York Times paper and view the paper, right? So that was democratization of information. But then the problem with the internet was that there was no way to make sure that this value does not get replicated, right? So I can, let's say there's a 100 rupee note, I create a copy of that 100 rupee note and send it on the internet. It doesn't have any value, right? So that is what blockchain, and that is what all these distributed ledger technologies bring to internet. They are essentially an internet of value, right? And these are some of the properties of a blockchain-based system. These are democratized, so nobody has a higher control over the network, because nobody actually controls the network. The transactions are transparent. There is a concept of pseudonymity, which means that there is an address which is assigned to me, but nobody knows who I am, or nobody knows that this particular address is assigned to me, and tomorrow I can change that address as well, right? So there is some amount of that is why it is called not completely anonymous, but pseudo-anonymous, right? Record irreversibility. There are multiple participants who are maintaining ledger entries within their systems, so that makes sure that if you have to go back and change a record, you have to change it across all of these ledgers, copies of which are available across the world, and we will go into details of how this system works, right? Robust and transparent. You have to have some way of making sure that the transactions which are being performed on a blockchain network and the transactions which are being stored onto a blockchain based system are robust and nobody can change them. Machine to machine collaboration is a very important aspect, and that is what makes it a very good solution, or a very appropriate solution for implementation of IoT specific use cases. And then of course peer-to-peer transmission, which means that if I am supposed to send value to someone else, I don't really need to go to a centralized organization. I can directly send it to the other person without the need of having the intervention of someone else in this transaction, right? So that is conceptually what blockchain is all about at a very high level, very high level rather. The way these systems work is that, let's say A wants to send money to B. There is a transaction which is created in the system. A lot of these transactions would get into one block. The block gets broadcasted to the entire ecosystem. All the parties involved in this entire ecosystem will validate the transaction, and once the transaction is validated, the block gets added and the money gets transferred from A to B. Now I'm giving the example of money here because we are talking about blockchain networks. There are distributed ledger technology networks such as Hyperledger, Quorum, and there's a host of other applications which are in use right now, which are not just focused on money part, right? They are focused on information. Now, this information can be coming from a device which is as simple as a mobile phone. This can be coming from a device which is as simple as a temperature sensor IoT device. And it can be as complicated as a SAP ERP system, which runs organizations which have net worth of billions and billions of dollars, right? So that is the beauty of this technology. It is totally agnostic to what kind of data stream you are putting onto this system, unless and until the data is coming from a reliable source. So what you will do is, if you have to make sure that you have, for example, the X 509 certificate for IoT device, you will have to somehow link the identification method of that particular IoT device with the blockchain network. So every time there is a data which is being sent by that particular device to a network, you know that, okay, this is the specific device which is sending the data. The data will be immutable because it cannot be changed. And the data will be secured cryptographically, so others cannot see it, but others can become a party to validating that data. And how does that happen is something that I will explain later, right? So it manages two things at the same time very wonderfully. One thing is, it makes sure that the transactions which are being sent are visible to the entire network, and the entire network is able to validate and verify those transactions without actually looking into the exact details of the transaction, right? And how that works is something that I will talk about in the upcoming slides. Okay, so first, we will specifically focus on the global blockchain network. Now, when I say the global blockchain network, I am talking about the network which runs Bitcoin, right? And there are three main components to this network. There are nodes. Now, these nodes can be any device that have sufficient memory and computation power, and any standard operating system, right? These nodes contribute towards running the blockchain network by contributing their memory and computation power, and in turn, they get a chance to earn Bitcoins, right? Now, all the nodes keep a copy of all the transactions that have taken place till now on the blockchain network, and constantly keep updating the list of transactions, right? So that means that there are multiple copies of all the transactions which have happened till now on the blockchain network created across all of these nodes. They use their computation power to try and earn Bitcoins, right? And thus they contribute towards running this particular network, because in trying to earn Bitcoins, they are essentially validating and verifying all the transactions which are taking place on this network. They are creating a linked list of sorts where, all the transactions are being stored onto the blockchain based system, and that is how they're making the network secure, right? There are more than 15,000 networks running across the world, and the map that you see on the right hand side bottom is a rough distribution of the entire set of blockchain networks, right? So you can see that these are distributed across the world, and it's very difficult to kind of take over this network because of that. And all of these nodes have a copy of the entire set of transactions, which is somewhere around 376 gigabytes as on 26 November 21. Then the and when we talk about, so that was about the memory that is required for running a node, right? When we go to the computation power that is required to run these nodes, or what is the amount of computation power which is on the blockchain network right now, to give you an idea of this, let's look at the definition of a hash per second, right? So every Bitcoin network has certain nodes running, and the combined computation power of these nodes is calculated in the form of hash per second. Now, 1 hash per second is essentially the computation power that is required to calculate a SHA-256 computation, right? Now, the total hash power of this blockchain network today is essentially close to 161 million terahash per second, right? So you can imagine what kind of computation resources and powers have been involved into this particular network. To put things into perspective, if and to explain how robust this network is, if someone was to take over this network, right, the one requirement is to make sure that they are able to they are able to control more than 50% of the nodes, which is the 50% of computation power on this network, right? So let's say if I was supposed to take over this network, I would need computation power which is more than 80 million terahash per second. To generate that kind of a computation power, I will need devices like this. There's a device called Antminer S3, which has the computation power of about 13 terahash per second, and this costs about $1,000 US, right? So you can do a price comparison of how robust this particular network is. And even if somebody was to take over this network, as I already said, all the data records of the transactions which have taken place are already stored with these 15,000 nodes which are running across the world, right? So even if there is one node which is live, and every or other nodes go down, even then this network can be brought back to life once again, right? So that is the kind of power that we are talking about. Now, every device signing into this particular network gets a set of public and private key, and I'm sure I don't need to explain what PKI infrastructure is to this audience. Essentially, you get a private key from the wallet that you create on this network. This private key is converted to a public key using elliptic curve cryptography, and then from that public key you generate an address which is SHA-256, right? So as the name suggests, the address and the public key is visible to the whole network. The private key is something which is of course private to you, right? And that is how you maintain the secrecy, or you maintain a control over the value that you have on this particular internet. The last and the most important part is the consensus algorithm, right? Or the consensus protocol. Now this protocol is to make sure that there is enough difficulty, or there is enough resources which are required to generate these bitcoins, or to generate the value out of this network, so that no one else can really take over this particular network. This is similar to making sure that the example that we started with, the example of Yap Islanders, it was required to go to an island which was about 400 kilometers away and generate these discs of limestone and then use them as a currency, right? So it was not possible for everyone to do this, and that is what we are trying to do using this consensus protocol for the blockchain network as well, right? The consensus protocol that they work on is called proof of work. It is all about finding the nonce, and what this nonce is something that I will talk about in later slides. So the amount of computation power that is required to calculate the nonce and prove that you have worked on this particular network and then get rewarded with Bitcoin was possible by using laptops or personal computers till about 7-8 years back. Then it moved to graphic cards, the ones that are used in typical gaming computers, and then it moved to specific devices like the ant miner that you see on your screen, right? So that is how the computation is becoming difficult on these networks, and that is why it was very easy to, let's say, generate a Bitcoin somewhere around 2007 or 2008, but right now it requires a lot of money and efforts as well. Okay. This slide represents how the PKI infrastructure works. It generates the process of public and private key generation. It is essentially a one-way street. So if you have the private key, you can generate the public key, and from the public key you can generate the address, but you cannot go the other way around. So right, so that is how it is made sure that your funds or your resources on this particular network, or the information that you're trying to exchange on this particular network, is controlled by you. Now, compare it with the IoT network. I can use the X509 certificate from my IoT device to generate this private key. And what that would mean is that every time my device sends the data, the network knows that, okay, this is a specific device which is sending this particular data. And tomorrow, if somebody is trying to tamper with this particular device, let's say replace this device with something else, or try to barge into the network and send a wrong data stream, and project that it is coming from the specific device, it is easily identifiable, right? So that is how it relates to a IoT network as well. Now, what we are talking in the next few slides is the entire transaction flow that takes place on a blockchain network, right? So let's go through this typical transaction flow. Assuming A wants to sell 10 Bitcoins to B on the blockchain network, which, by the way, will be about 4 crores in Indian rupees, as a single Bitcoin today costs about 40 lakhs in value, right? So that is the type of value exchange that happens on this particular network right now. So A will enter the details of this transaction into the blockchain network. The node to which A is connected to will combine A's private key with the transaction details, right? Now, this transaction detail will say that, okay, I am A and I want to transfer 10 Bitcoins from my account to B's account, right? Then there will be a creation of a digital signature by the Bitcoin client, which is installed on the laptop or the device that you're using. This digital signature is a unique digital signature. So just like a physical signature, which is done on a piece of paper for a specific purpose, you cannot really copy this digital signature and use it for some other, to perform some other transaction, right? So that is something which is very important. The second part of this transaction is the digital signature created in the previous step is added to the public key of A, right? And a combination of these two details is announced to the entire blockchain network of nodes. And this goes and gets recorded into a pool of transactions, which is called the mempool, right? So what has happened till now is that A has generated a transaction, added it to its private key. and created a digital signature out of it. This digital signature is combined with the public key of A, which of course the entire world knows. And this combination of digital signature with A's public key is going into a mempool, right? We call it mempool because it is just a pool of transactions which are waiting to be validated and added to the blockchain, right? So it's a FIFO algorithm in which the transactions go in and then they go out in the order which they have entered. So a lot of these transactions will keep on happening across the world. When the number of transaction reaches 1 MB, that is when a new block creation happens, right? Because that is how this entire network works. The total size of one block is supposed to be only 1 MB, right? And now after the creation of this particular block, it is ready to be validated by the network. Now, this is when the validation part starts, right? So the set of digital signature with public key is announced to the entire blockchain network. Now, this blockchain network goes to the entire set of nodes, and now this is the next step, right? So in the next step, the nodes will receive the block, and now they will validate all the underlying transactions within the block, right? So like, for example, in this block of 1 MB, there are thousands of transactions. One of the transactions is the transaction which A is trying to do, the transfer of 10 Bitcoins from A's wallet to B's wallet, right? The nodes will do two simple things here, right? Is A claiming to be who A is? And do they have the required amount of Bitcoin in their wallet that they're trying to send to B, right? Now, because we are talking about the blockchain network, we are talking about transfer of Bitcoins. Had A been an IoT device, what the network would have done is they would have validated if A is the IoT device which it claims to be. And secondly, does A have the data in its wallet which is trying to send to B, right? And if everything is fine, then this transaction is validated and this transaction becomes a part of the formal block creation process, right? Now, this is where the beauty of blockchain comes into picture. The nodes know only the digital signature and the public key of A, right? However, they can validate without knowing A's private key, that the private key that was used to make this particular digital signature actually corresponds to the public key that came attached with the digital signature. Okay, so because this is important, I'll repeat this again. The digital key, the digital signature was used, was created by using the private key of A. The same private key was used to create the public key of A. The entire world knows the public key, and the entire world knows the digital signature. And now, by knowing the digital signature and the public key of A, they are trying to validate if A is the person who A claims to be by doing a verification of the private key, right? So essentially, they do not know the private key. Without knowing the private key, they can figure out if the public key was generated by using the same private key which was used to generate this particular digital signature, right? So this is where a combination of being able to verify and validate a transaction without really getting into the transaction detail comes into picture, right? And that is what makes this network unique. So you do not know what is the actual data behind a transaction, but still you are able to validate the transaction as to where this transaction is coming from and is the transaction accurate and fine in every way or not, right? So that is a very important concept about blockchain. After this verification is done, the block gets added to the existing chain of blocks, right? And this is something that we will explain in the next slide. Okay. Now, this slide is the representation of blockchain. It can be compared to a linked list. So every block in blockchain has a list of transactions. The total size of these transactions is 1 MB. These transactions are combined with something called as a nonce, right? Now, nonce is a very critical concept that we will discuss in the upcoming slides. The calculation of nonce is the part that requires the extensive amount of computation power that we had been talking about, some time back. And this is where the proof of work algorithm comes into picture, essentially, which means that there is a proof that a lot of nodes have actually worked to create this nonce, and it is not a very simple task to do, which essentially makes this network very strong, right? So we have a set of transactions in the body of the block, and nonce is the header of the first block. Now, a combination of these two things, the header and the body, is converted into a string of 256 characters by using SHA-256 algorithm. It is this string of 256 characters which is updated into the header of the next block, right? So essentially what we have done is we have created a fingerprint of block number 1, embedded that particular fingerprint in block number 2. Now, when we create a fingerprint for block number 2 while creating the block number 3, that fingerprint will essentially have a representation of all the blocks which have been created in the past. So if anybody has to go back and change a specific transaction in a block that has been created in the past, you will have to change all of these fingerprints, right? So if I was a malicious actor and I had to, let's say, and if I wanted to go back and change a transaction in block number 2, I cannot do that because the fingerprint of block number 2 is added in block number 3, the fingerprint of block number 3 is added in block number 4, and so on and so forth, right? So this is what makes it extremely robust. And this is what makes sure that the data which is going onto a blockchain-based transaction is immutable. So nobody can go and change it. The data updates are consensus driven. So all of these nodes reach a consensus, and then only then they approve, that a particular transaction is validated and it can be added onto a blockchain-based system. There are multiple copies of this data created across the world. We were talking about the 15,000 nodes that are existing and running as of date. So you have 15,000 copies of this, these sets of data across the world. This is decentralized, which means that there is no central body controlling it. So there is no chance that there is a body which controls it, and if that body goes down, the entire data is lost and things like that. It is distributed, which essentially means that the computation power is spread across the world with these 15,000 nodes, right? So even if there is, let's say, one node left, there is a bright possibility, or rather it is possible to bring this network back into action again, right? So that is what makes the blockchain network extremely reliable, trustworthy, robust, and it ensures data security, right? Now, these are the characteristics which make it extremely valuable as a global network, and they also make it extremely valuable when it comes to the scenario of implementation of IoT devices, right? Because you are able to verify the data which is coming from IoT device. You are able to verify that the device which is sending the data is the actual device which is supposed to send the data, and there is no foul play there, right? The data that comes, every single transaction detail coming from IoT device is getting stored onto a blockchain-based system. So, there is no chance of data loss happening here. The data cannot be changed. Data is immutable, right? So any data that comes from an IoT device goes into a permanent storage system, and there is nobody who can actually come and tamper with this whole scheme of things which is going around, right? So excuse me, that is what makes the blockchain system extremely valuable for IoT use cases, right? So let's go into what a nonce is, and let's talk about what is the exact computation and what is the exact requirement which is making this blockchain network such a phenomenal system that is existing today, right? Now this slide represents what the nonce exactly is and how it makes the network secure. When we try to add a new block to the blockchain, we have two data fields that you see on your screen, right? The hash of the most recent block which has been added to the network, and the set of new transactions whose size is 1 MB. Like, for example, one of the transactions that we were talking about was the willingness for A to transfer 10 Bitcoin from A to B's wallet, right? So just like that, you have multiple transactions which have been added. As I again mentioned, we are talking about transfer of Bitcoin. A transaction can also be when, let's say, my refrigerator has an IoT device which keeps on giving me updates about temperature after every 15 minutes. So that can also be a transaction, and that will be validated in the same way that the transaction of 10 Bitcoin is being validated, right? So as I said, we have two data points here. One is the hash of the previous block, and the list of new transactions which are to be added into the new block that we are trying to create, right? Now, what happens is that this is where the blockchain network gives you a challenge, right? The challenge is to somehow get an outcome from this SHA-256 algorithm in the form of a string of 256 characters, where the first few characters are 0, right? Now, when I say first few characters, let's assume that this number of characters is X, right? And the more the requirement is, to have zeros at the start of the string as an outcome of SHA-256, the more difficult this calculation starts becoming, right? Now, what you have to do is you have to combine the two fields, the hash of the previous block and the new transactions. And the challenge is that you have to generate a SHA-256, outcome of a SHA-256 algorithm, where the first few strings are zeros, right? Now, this number of zeros that is required is X, and this defines the difficulty level, right? So for example, if let's say there are 100 nodes today and they have certain amount of computation power. Tomorrow, if there are 200 nodes which add on to this particular blockchain network, the computation power will increase, and so will the difficulty, right? So for example, today the requirement might be to make sure that the first two digits are zero. Tomorrow the requirement might be that the first four or the first 5 digits are zero. Now the reason why this is done is to make sure that it is difficult to find the nonce, and with that difficulty to find the nonce comes the robustness in the network, right? So when we compare this to what Yap Islanders were doing in around 500 AD, they were making it extremely difficult to create the stone money, right? And what blockchain is doing right now is it is creating it very difficult to do this particular computation. And in order to do that, these 50,000 nodes race with each other to create a nonce, right? Now, what happens is that when you add nonce to these two values, hash of the previous block and the set of new transactions, you are supposed to generate, as I said, using SHA-256 algorithm, a string which has a certain number of zeros initially. Now, as you would all know, SHA-256 algorithm cannot be tampered with. And the only way that you can generate a desired outcome from this calculation is by a brute force method, or by trying different combinations of numbers, right? Now, these combination of numbers is called nonce. So essentially, nonce is a value that is added to these two values. These two values are known, the hash of previous block and the new transactions. When you add nonce to these values and you apply SHA-256, you should get a string of 256 characters. Starting digits of those 256 characters should be 0, right? Now, how many digits should be 0 is something which is defined by the algorithm, right? So what the algorithm makes sure is that one block is getting created after every 10 minutes, and that would depend on the how tough this particular computation problem is. So essentially, if let's say there is there are 15,000 nodes today working to solve this problem, and it is taking about 10 minutes to solve this problem right now. Tomorrow, if there are 5,000 extra nodes which get added, it will mean that the computation power, the overall computation power in millions of terahash per second has increased, right? The algorithm will automatically realize this, and it will see that the time required to calculate this nonce has decreased from 10 minutes to say about 7 or 8 minutes, right? It will automatically increase the difficulty at that point. So it will say that instead of first 3 digits being 0, now I want you to calculate a nonce that will make sure that the first 5 digits are a 0, right? So that's the whole beauty of this blockchain algorithm. It is a self-maintained algorithm which is decentralized, distributed, and it is autonomous. So nobody has to intervene in the way this particular network works, right? So that is the power of this algorithm that comes into picture. And please feel free to interrupt me if you have any questions, because this concept is really very important, right? So this is all about how a blockchain network is created, what is the type of computation that multiple nodes are required to do, to earn these bitcoins. And it's and one very important part, whenever a node is able to find this nonce, the block which we were trying to generate gets added onto the blockchain in the form of the linked list that we discussed in this particular slide, right? So you have one more block which gets added, and the network, or rather the node which has actually been able to find this particular nonce in competition with the 15,000 other nodes which are on this particular blockchain network, gets a reward of about 6.5 Bitcoin, right? Now this is 6.25 Bitcoin, right? So this 6.25 Bitcoin, you can imagine what value of those Bitcoins would be today, because one Bitcoin is about 40 lakhs Indian rupees as on date. So this is the kind of incentive which is there on this particular network, and this is what motivates organizations to be a part of this particular blockchain network, which is public in nature, right? So anybody can download this blockchain, anybody can become a node, and anybody can start, utilizing their computation power in a race to find the nonce and thus get Bitcoin, right? So this is how this entire network works. Now, moving on to the next slide. So this is what has been wonderfully done in this particular blockchain network. I am sure you would know that the entire blockchain algorithm was created by someone called as Satoshi Nakamoto. Now, we don't know who Satoshi Nakamoto is. It can be, one person, it can be a group of people. Nobody knows who this person is, where this person is from. There are some speculations, but nobody knows for sure. The reason why this person is anonymous is because he wanted this entire network to be decentralized, disintermediated, and distributed. So if there is no single point of failure, there is no one who can stop this network in the world, and there is nobody who can control this network, right? So that's all about the blockchain network. Now, what this does is this ensures that the data which is on the network is immutable. It is consensus driven. There are multiple copies. The whole network or the whole data storing mechanism is decentralized and distributed. The computation which is done on this network makes sure that the network is self-adjusting, right? So as we talked about the nonce, as and when the computation power being deployed on this particular network goes up or down, the difficulty level changes accordingly. The objective is to make sure that every new blockchain, every new block that is added onto the blockchain network gets added only after 10 minutes, right? That is to make sure that there is certain amount of computation, there is some certain amount of work, or there is certain amount of effort that has gone into creating a block, and that makes it extremely difficult to tamper with this particular network, right? So essentially, in a nutshell, what Mr. or Miss Satoshi Nakamoto did was they combined cryptography, using advanced cryptographic methods such as the SHA-256 algorithm or the elliptic curve cryptography, to make a secure network, to make sure that the data was secure. And they also made sure that this was designed in a way that whenever a transaction has happened, people are able to validate that transaction without knowing the exact details of the transaction, right? So that was the brilliance of the design of this particular network. They came up with game theory, which essentially, the most basic principle of game theory is the fact that if there is a group of individuals, people will work for a common benefit of a common cause if they find that that common cause is benefiting them in return, right? And then they embedded the value of economic incentivization into it as well, right? So I'm not doing this for charity. Let's say if I had an Antminer S9, I would put it onto the blockchain-based network, and I would get some fraction of Bitcoin, and I would earn money out of it, right? So that is the economic incentivization. So that is the reason why this network is becoming bigger and bigger with every passing day, and that is the reason why it is getting so much attention, right? Now, the blockchain network that runs Bitcoin is the most primitive and the most basic use case of this technology. What has happened after this is that people realize that this particular network was suitable for a certain set of use cases, right? So you can create value, you can store value, and you can transfer value on this network in the form of Bitcoin, right? But the problem was that what made this network extremely robust was the simplicity of this network. There were certain set of transactions which could be done. This network was not, the programming language that was used to create this network was called Forth, F-O-U-R-T-H, and this language was not Turing complete, right? So a lot of attacks such as the denial of service attack, infinite loop attacks, and things like that could not be done on this particular network, right? So the simplicity of the network made it extremely robust. However, the challenge was that in spite of the fact that this being a very robust network, there were a set of, there were a number of use cases which required certain logic to be embedded into this network. And there was no way that you can embed logic into this network. You can only store value, you can only transfer value on a blockchain network using Bitcoin, right? Now, in order to overcome that, people started coming with more advanced ways of, running this decentralized network of nodes. And when people started coming up with these kind of systems, it was able to draw the attention of enterprise ecosystem as well, right? So let's say there's a supply chain. There are 20-25 organizations which are a part of this particular supply chain, because supply chains today are no more controlled by one organization, and we will go into the more details later. There are a certain set of transactions which all of these participants have to see, right? What happens today is that all of these organizations are connected to every other organization as a point-to-point communication, right? And any single transaction which everybody has to see has to go through emails, or go through EDI or XML interactions across the ERP systems that are installed across all of these organizations. So that becomes a very difficult task. There is problem of data security. There is problem of data transparency as well. So that is where the enterprise blockchain systems, which we call them, started emerging, right? And we will go into the details of those in upcoming slides. So this was all about blockchain. Now let's talk about the enterprise systems and how blockchains are being used. Okay, and this is how we can draw a parallel between what YAP Islanders did versus what blockchain is doing today. In a way, both of them are recording all the transactions. There is a shared transactional ledger. The difference being that in the case of YAP Islanders, there was a group of elders who was maintaining this. In the case of blockchain, there are about 15,000 nodes which are doing this globally. The expensive resource that was used to create value in the case of YAP Islander was, your ability to go to a distinct island using very basic boats and then create a limestone disk of about 200 kilograms and get it back. In this case, it is the computation power which is required to create these Bitcoin. And then, of course, there are multiple copies, which makes the data immutable. This is decentralized, distributed, consensus-driven. And the biggest advantage that blockchain gives you is that the data is cryptographically secured, right? So using advanced cryptographic methods, as I said, like SHA-256 and elliptic curve cryptography, you make sure that the data is secure, right? So this is, what makes this entire world of blockchain very interesting, because the concept, if you look at it, is very simple. And the tools and the techniques which have been used to create this network is very simple, but this is having a profound impact on the way businesses are being conducted today. Okay, so let's move on to what distributed ledger technology is. So as I was talking about the blockchain network, and I was trying to draw comparison between the blockchain network versus the other networks, the most prominent network today is something called as Ethereum. On blockchain, you need Bitcoin, which is used to store and transfer value and to perform a transaction as a fees. On the Ethereum network, you need Ether, right? So Ether is the coin for the Ethereum network. It is more like fuel that runs your vehicle. So you need Ether to run Ethereum, right? Now, the difference between Ethereum and blockchain is the fact that blockchain is simple, robust, and strong because it is very simple. Ethereum is programmable, right? So there is a language called Solidity on which you can develop codes and programs, and these programs can be embedded into the message and the data that all these nodes are running, right? So let's say I have created a program to, I've created a calculator, right? And I have posted this particular calculator on the Ethereum network. This will be a distributed and decentralized program which will go to all the network nodes, and all the network nodes will be running it. There is a concept of EVM, Ethereum Virtual Machine. Now, this machine works as a combined compute as a machine which draws the computation power from all the nodes which are a part of the Ethereum network, right? So earlier, when in Bitcoin, the node were contributing their computing power and calculating nonce. On Ethereum, these nodes are contributing their computing power to run programs, right? So let's say I've created this calculator, I have sent it on the Ethereum network. The network hosts this particular calculator for me. And tomorrow, if you have to do a calculation, in order to use that calculator, you have to pay certain fees, and that fees will be in the form of Ether, right? So that is how the token economics changed from blockchain to Ethereum. And the interesting part is that a lot of networks that you hear about today, like Ethereum, Monero, Ripple, etc., are actually different types of or rather they have the same concept that Ethereum has used. There is a way of running programs, there is a way of building logic into these networks, there is a way to have different organizations become a part of this network, and all of these organizations to use a certain program which is embedded into this network. Now, how does this work in a real life scenario, or how can you use to automate process, or how can you use it in a typical business scenarios like this? In supply chain, there's a lot of material movement that keeps on happening, right? Now, every time there's a material which goes, let's say, from the manufacturer to the consumer, there is somebody who's sitting on the manufacturer side making a note of the material movement. The material is handed over to the driver of the truck who's transporting it. On the other side, there is someone else who takes ownership of this particular material, makes a note again, and this entire process is extremely complicated because there are purchase orders, there are invoices, there are different ways and means through which products are being tracked. So not every organization would have IoT device, right? So you have IoT device into a product, you have barcode readers, you have RFID readers, you have RFID sensors, etc., which capture information from different points of this entire product movement, right? Now, there's a lot of manual intervention required. You get this data, you enter it into the system. There is a huge chance that the product might have actually moved, but the information about that product has not moved to the next handover point. Now, this creates a lot of issues in supply chain, and that is where a use case like Ethereum comes into picture, right? So what I would ideally do is I would, let's say, have an IoT device embedded into a product which is manufactured by the manufacturer, and that particular IoT device starts sending data to the Ethereum network. All the participants who are a part of this supply chain would form that particular Ethereum network. So whenever there is an update coming from this particular IoT device, the entire network gets to see that update in real time, right? So that is a very basic concept of how this particular Ethereum network can be used. There are other types of networks also. So for example, just like blockchain is a public network which can be joined by anyone and anybody can view the transaction, Ethereum is again a public network, but there is a private version of Ethereum also, which is called Quorum, right? So what I can do is I can create a network within a set of 4 or 5 organizations, and I can run that particular blockchain on my Quorum network as well, right? So that would be a decentralized distributed network in the sense that only those 4 or 5 organizations would have access to the data, and only those 4 or 5 organizations will be able to view the data and make transaction validations, right? So that is how this entire focus moved from value creation and value exchange on blockchain to having a network which is decentralized, distributed, and a network that is capable of running programs as well, which are developed by a Turing complete language called Solidity. Okay, so at a high level, this is the difference, and this is how the evolution has happened of all these networks. There are different types of networks. There are public networks which anybody can join. There are public permissionless networks which anyone can join without any kind of a permission. There are private networks which keep the data secure. Private permission networks wherein you need permission to join the network. So let's say there are 4 or 5 organizations who have created a network and they are running Quorum in the private permissioned area. So if I am a new organization and I want to join that particular organization, I will need permission to join the network and then view the entire transaction details which are happening, right? So what we are essentially doing is we are creating localized versions of the public blockchains, like blockchain, the network that runs Ethereum, the network that runs Bitcoin, or Ethereum as such, right? So that is how this private permissioned network came into picture, and that is how organizations started using this for their own business processes, right? So let's look into why IoT and blockchain are such a great idea. The image that you see on your screen right now is, it must be about 100 years old, when there was a plant by Ford. This was called Ford's River Rouge plant. The interesting part about this particular plant was the entire value chain of manufacturing of a car from end to end was controlled by Ford, right? At that point in time, supply chains used to be a linear set of organizations, whereas and when I say supply chain, I'm not just talking about the network which transfers goods, right? I'm talking about the entire network which creates products and then sells it off to their customers, right? So you have people who are extracting minerals, raw materials, people who are making rubber, etc., for creation of a car, and once this vehicle is manufactured, they are selling it to the customers, right? So that is the entire supply chain. Now, about 100 years back, it was fine because the organizations at that point in time were vertically integrated. There was no need to collaborate with other organizations in the world. But what has happened now is that these supply chains have moved on to become supply chain networks, which are global organizations spread across the world, which are involved in the production and distribution of products. And there is huge competition between these organizations. There is a need to share data in real time. And when I say share data in real time, what typically happens is that, let's say there's a tier 1 supplier for example, Maruti Suzuki, right? Now, this particular tier 1 supplier might be making tires for Maruti Suzuki. They might be making tires for Honda. They might be making tires for Tata as well, right? So there is a need to establish communication between these participants at the same time, and there is also a need to make sure that the data that these participants are sharing with each other does not get into the wrong hand, right? So for example, if the tier 1 manufacturer sets a tire to Maruti, Tata should not know about it, right? And if they are sending a tire to so let's say Honda, Tata should not know about the transaction which is happening between these participants, right? So you need certain amount of data privacy and you need certain amount of transparency as well, which is very difficult to maintain in the current implementation of ERP systems, because these are all vertically integrated systems where organizations don't really talk to each other that well. Okay, and one of the reasons also why supply chains were fine, say about 100 years back, was because those days it was not a very customer centric market, right? It was a seller's market. So Mr. Henry Ford famously said that any customer can have a car painted in any color as long as the car is black, right? So it was not, the power was not much in the hands of the buyer, and the situation has changed now, right? Now these are some of the typical challenges which supply chains of today face. Supply chain resilience, because what happens is that most of the supply chains today are dominated by one major participant, right? So for example, let's say if there's a supply chain which is maintained and operationalized by Walmart, and there is a supplier of Walmart sitting out of Bangalore or out of Bhopal, that supplier will not have a say in the network, right? So, and that also creates a single point of failure. There were examples like the network of Target, the retailer, was attacked in US from one of the supplier nodes that was connected to their network. There was a major disruption that happened in the AP Molar Maersk network few years back, and their entire logistic operations went down. So the problem is that it makes sure that your supply chain network does not remain resilient. There is single point of failure, and the control is held by one single organization, right? So that creates multiple issues. Business to business integration, when there is one single participant controlling this network, there is no communication between other participants on a one-to-one level. Machine to machine integration, you have IoT devices. Let's say the third party logistic provider has deployed a certain type of IoT devices into the system. The data from that IoT device will come to the third party logistic provider's ERP system and then to other organizations, right? So you are not really utilizing the IoT devices in the way that they should be. Supply chain traceability, in the sense, you don't have systems which give you the traceability to a single product unit level, right? You have traceability to, let's say, a shipment level, to a pallet or a carton level, right? And then of course there is a lot of money and effort which goes into making sure that the different types of data streams which are coming from a typical supply chain are reconciled, right? And there is issue around data silo creations, right? So you have different data streams stored in different IT systems of different organizations, right? And then there is a lack of single source of truth. So these are some of the typical challenges that supply chains of today face. This image will help you visualize how supply chains work, right? So you have a supplier, manufacturer, distributor, and retailer. Because they are on different supply chain management systems, they are performing point-to-point data interchange, right? So data from supplier is going to manufacturer, but then what data is flowing from supplier to manufacturer, the retailer does not know, right? Unless and until the supplier actually goes and tells retailer about this particular information flow, right? So these are a lot of challenges, and on the bottom of your slide, you see challenges because of those issues, right? So for example, because there is a point-to-point data interchange mechanism between the supply chain management systems, there are disconnected information islands. There is disintegrated supply chain flow, because every supply chain has three types of flows: the product, inventory, and financial flow, right? And then there is a limited scope of audit and scope of root cause analysis as well if something goes wrong. There are digital gaps across these participants that leads to a lack of connection between analog and digital. So I may have excellent digital manufacturing veins of method, as per industry 4.0, but when it comes to transferring of that data to my manufacturer, most of the time I would generate a report and create a paper copy of that report, give it to the driver who's taking that particular material, and then send it to the manufacturer, right? So essentially there is a complete discordancy between these systems. There is a lack of process automation that I can achieve. And of course, you have different organizations using their own supply chain management systems that would lead to a lack of decentralization in these networks, right? So multiple organizations have their own data silos, their islands of control, and they don't become a part of one complete ecosystem, which is something which is extremely critical these days when it comes to supply chains, right? Now, what a blockchain-based system would do is that it would work as a simple integrating layer across all of these participants of the supply chain system, right? There would be a central point of information, a single source of truth, because all the transactions are getting updated onto the blockchain-based system in real time. Now visualize this when I was talking about the nodes which are there on the blockchain-based system, right? You have all these nodes who are involved in collaborative decision-making, transaction approval, and they all share the same set of transaction details, right? So there is one copy of this data which is shared across all of these participants, right? So there is, a single source of truth, which is very important. All of these data points are getting updated in real time. So this data can be, data about purchase order movement, data about inventory movement. This can be data about, let's say, that a particular product was ordered by somebody living in Bangalore to a manufacturer based out of Delhi. The moment the manufacturer has manufactured that particular product, the customer gets to know that in real time, right? So those are the type of scenarios that are covered. There's a lot that we can get into, but then because of the time constraint, let me just move on to the next slide. Now, I wanted to spend some time in this particular scenario. We are talking about how IoT and blockchain has been used in the cold chain tracking scenario, right? And this slide is a view of how inefficient the cold chain tracking system today is, and I hope you all understand what is a cold chain tracking system. As the name suggests, we are talking about the products which are sensitive to temperature or the ambient conditions in which these particular products are moved around, right? So you have food pharma chemicals, which are the prime examples. There is certain amount of, certain limit of temperature and humidity in which these products are to be transported. You have to make sure that these products are continuously maintained in that particular temperature or humidity or other conditions, right? The challenges are there because most generally the loss of life is there if there is some kind of a variation in temperature in pharmaceuticals. These products have very short shelf life. There are product specific requirements. So one vaccine would, let's say, require temperature of 1 to 5 degrees. The other one could require temperature of below 0 degree and things like that. Brand protection is a big problem. Let's say if I'm a manufacturer of a temperature sensitive product, I have given it to my logistics service provider, and because of their fault, there is an issue with the quality of my vaccine. It is my brand which suffers, right? And there is no way I can go and make that person liable. Compliance is a big problem. There are acts such as DSCSA, FMD, GDP, which is the good distribution practices in India. There is something called as EU MDR, which is around medical device tracking in Europe. Now, these acts make it mandatory for the entire set of participants which are a part of a value chain to make sure that the data of a single product which is transported and is critical is stored into their systems, right? And of course, making these products and then these products going waste is a resource wastage, right? So those are, and there is a lack of trust if something goes wrong in your temperature sensitive product, right? And what happens is that there is inefficient monitoring today because most of the systems that work towards monitoring these temperatures in a supply chain are data logger based systems. So you get to know if there is some kind of an issue with the temperature in which the vaccine was to be transported only once the vaccine has reached the end point, right? And in order to do a manual reconciliation and trying to figure out why something went wrong, it's a huge task, and there's always a problem of doing root cause analysis as well. You would know that there has been some problem, but it's very difficult to find out who was responsible for it and things like that, right? Okay, so this slide talks about a typical example of COVID vaccines. As I said, every COVID vaccine requires us a very specific temperature range to be transported. There is a requirement to give a repeat dose to the same person of the same vaccine, which reduces the flexibility in the supply chain. The supply chains are fragmented. You have multiple participants transporting these vaccines across different modes of transport, right? So you have trucks, you have airplanes, you have ships, etc. And the temperature measurement system must be a system which can, take care of all of these requirements. Now, the reason why it is difficult, as I talked about data logger based systems, there is inefficient tracking because you get to know about a temperature variation only when the vaccines have reached the end, end stage. you are not able to handle these products at a unit level, because many a times the temperature recording and updation happens only at a container level, or at the level at which these are transported in a shipment, right? There are hot and cold zones. So in every container there are some areas which are cold, there are some areas which are hot. That leads to a lot of variation and issues. These systems are centralized, so I have a third party logistic provider who's transferring these temperature sensitive vaccines. They would control the data which is coming from the IoT device being deployed on these vaccines to measure the temperature, right? And I, as a manufacturer, will get to know this data only when the vaccines have reached the endpoint, and I will have to depend and I will have to trust that particular manufacturer, the third-party logistic provider, right? And of course, if there is a lack of real-time update about the products which are moving across in my value chain, if there is any kind of a change which has happened, in the supply chain, it is very difficult to figure out what that change was in real time and prepare myself accordingly, right? So these are some of the key issues which are there in today's systems which are aimed towards tracking COVID vaccines. Now, the project that I'm talking about was done by integrating IoT devices with a blockchain-based system. Now, the problems that the customer was facing was, of course, they needed a real-time update of temperature and humidity. They wanted this data to be uploaded and shared in real time with all the participants which are a part of this entire supply chain of COVID vaccines, which included the manufacturer, third-party logistic provider, the dealer distributor, and finally the retailer, right? They needed real-time alert generation. They needed product tracking to be done at a smallest product unit level as well, right? So they wanted to make sure that the product can be tracked at, let's say, a container level or a box level, a carton level, or a single product unit level. They wanted this solution to work across all the different modes of transport. They wanted aggregation and disaggregation, which was very important, because let's say I have transported 50 boxes of vaccines from my warehouse to an airport. 25 of those boxes have gone to one flight, and the other 25 have traveled ahead on road, right? So that is the type of scenario that they wanted this particular solution to take care of. Of course, report generation and sharing of these reports and alerts in real time was very important. They also wanted some mechanism through which they can do a counterfeit detection, right? So if there is some kind of a forced opening of a box and somebody replaces the original vaccine with a fake vaccine, they wanted to track that as well. And of course, these had to be DGCA compliant as well, right? So these had to be transported by air, and you had to make sure that any device that we are using adheres to the DGCA norms as well. Now, what you see on the bottom of your screen is a high-level architecture of how this solution works. On the left-hand side are the sensors. Now, these sensors are capable of recording temperature, humidity, tamper, which is the light sensitivity, right? So these sensors would be placed inside the vaccine boxes, and if there is any kind of a forced opening of the box, there would be a change in the light intensity, and that would create an alarm, right? These sensors measured shock and vibration as well. There was an ability to measure magnetic field. So you can place a sensor on one side of the door of a truck, you can place a magnet on the other side, and the moment that truck is opened, the sensor would raise an alarm. These sensors also measured atmospheric pressure and speed, right? So the moment the devices go onto a flight, they automatically switch off to the flight mode, right? And of course, there was geolocation. These sensors and the IoT master that you see on the screen in the center had their own memory and power as well, right? So there was no way that the data could be lost. Now, these were IoT devices. The sensors were connected through a Bluetooth enabled link to the IoT master. This master was essentially called as hub, and this hub was capturing data from these sensors in two ways, right? There was something called as a guest mode. There was something called a paired mode. You pair all the sensors, a specific number of sensors to this hub, and then the hub will take data from only those sensors to a Bluetooth link. And there was a guest mode. So you have, let's say, 50 devices around this IoT hub, and that would keep on scanning the environment around it and picking up data from all the sensors which are around them and storing it and then sending it ahead. Once the data from these, and then so that would the guest mode or the paired mode would depend on the length of the journey, the logistic requirement of the customer, and also what was the power backup available, right? So if you have the capability to attach this particular hub device to the power of the vehicle in which it is moving, it is fine. You can use any mode that you want. But a hub, a guest versus a paired mode, which would always take more energy, because there was a continuous tracking of devices, right, in the guest mode. This data was received into the hub, and you could configure as to what was the frequency with which the data calculation and transferring of data from sensor to the hub was happening. In our case, data was recorded after every 5 minutes by the sensors, and after every 15 minutes, this was sent to the hub. The remaining 14 minutes, the hub would be in a sleep mode. It will wake up again. It will send this data again, right? Now, this particular data was received in hex format from the hub to a Azure IoT hub system. We had, and it was using MQTT protocol. We were using the parser logic, which was built into the Azure IoT hub. And the parser logic was essentially required to make sense out of the 14-digit hex key, or rather the hex format in which this data was being sent, right? So you would know what was the exact temperature, humidity, if there was any kind of alert, etc. on the way while these products are moving from the hub, and that gets recorded into the Azure IoT hub. Now, the entire data set was being stored onto a Azure memory blob. Only the aberration in that, aberration in the defined range of temperature or humidity was reported onto the blockchain-based system. This was done by a certain number of cron jobs which were running in the background. Now, this logic was built into the blockchain-based system. So what happens is that there was a quorum-based blockchain which was running in the backend. It would get the data from the Azure IoT hub. The cron jobs would say that, okay, there is a variation in the temperature. The Ethereum blockchain, or rather the quorum blockchain, would pick up that data and immediately transfer it to all the 4 nodes which are involved. Now, the nodes in this case were manufacturer, dealer, distributor, logistics, and retailer, right? So all of these participants get to see every single set of detail that is happening, on the ground for each one of these vaccines. Now, I put one sensor into, every vaccine box. I have a capability to track each and every single vaccine box from the point of manufacturing till the point it is being delivered to a hospital in real time. Now, what this does is, of course, it gives me a real-time update at a single product unit level. It also makes my supply chain proactive, right? So let's say there are some vaccines which have started from Hyderabad, and they are supposed to reach Bangalore, let's say 4 days from now. If something goes wrong on day 1, the retailer, the logistic provider, and the dealer distributor, everybody gets to know this on day 1 itself, and then they can immediately call the driver to fix that issue, or they can ask the driver to go back to the manufacturer and get a new set of vaccines, right? So that is how my supply chain became proactive. The issue with liability management was also taken care of. Let's say if the vaccines were with the logistics service provider, and something went wrong on the way, the data became immutable, right? So every single transaction which is coming from the IoT device is going to a blockchain-based system where the data immutability is achieved. So the third-party logistic provider cannot really go back and say that, this particular issue which happened with the vaccine was not my fault, right? And they can be made liable, they can be held responsible for a specific issue that has happened. So that is how you can do a root cause analysis as well. We had the capability in this system to send SMS and email based alerts. You can configure this system in whichever way you want. You can send SMSs about any kind of a data, any kind of aberration that has happened while the vaccines were moving to, let's say, the supply chain managers after every 15 minutes. Let's say if that particular issue is not fixed in the next 4 or 5 hours, you can send this particular alert detail to the CEO of the organization. So that's how this system was configured. We had geo-fencing and geo-tracking capabilities as well. So let's say the products are moving from Delhi to Bangalore. I can create geo-fences in Bangalore and Delhi, and I can create geo-fences on the way, which shows that, okay, this has left Delhi now, this has entered Bhopal now, this is leaving Bhopal, this is reaching Bangalore, this is, exiting Bangalore, geo-fence and stuff like that. I can create geo-fence for the route which the truck is supposed to follow. And all of these details are coming in from IoT devices to my blockchain-based system. Every single transaction is getting recorded. Every single participant who is a part of this entire value chain gets to view these transactions, and the action that is taken in real time is also getting updated onto the blockchain-based system, right? So that is how, that is all about a real-time implementation of a blockchain and a IoT based system used for tracking COVID vaccines. So I hope this made it clear for you the transformational impact that the IoT that is coming in from the integration of IoT and blockchain in the enterprise world. Moving on to the next slide, this is how this entire solution works. So like I'm pretty sure all of you, it must be very clear to all of you by now. Part number one is device tagging, wherein you can place the sensors inside a pallet, carton, box, or a product unit level. The sensors will get linked to the ID, or you have a ERP system running. So the sensor has a number, the product in which it is going has a number as well. These two numbers get linked to a specific these two numbers get linked and they get stored in a SAP based system. Once this happens, there is hub association, right? So you start placing these shipments into a truck or into a flight, and the product will start moving. After that, you have disintermediation, disaggregation and aggregation as well. So let's say if there is some kind of a 10 products have to go onto a flight, they would be placed on a flight, and the moment they are delivered on the other side, you would start disintegrating these products and keeping the IoT boxes and the hubs separate, and you can recharge them and you can send it back on the reverse logistics to the manufacturing unit again, right? So that is how this entire cycle works, and this IoT devices become reusable, right? So this is how the COVID vaccine tracking solution utilized IoT and blockchain based system to create a end-to-end visible system of value interchange at a product unit level. Now, these are the benefits which all of these participants get from this particular system. It is very obvious for the pharma manufacturer. They are able to protect their brand. If something goes wrong, they know who's liable for it. They have an end-to-end visibility of inventory. There is anti-counterfeiting and tamper-proofing as well. The dealer distributor, for example, gets to have an end-to-end visibility of the inventory that is moving across. They can prepare themselves proactively for a supply chain shock. The logistics service provider, again, improves the efficiency of the entire supply chain operations. You are seamlessly getting data about every single product. You are getting every single details about the products which are moving across. There is real-time alert management. So let's say there's a driver who's driving a truck and these products are placed onto the truck, and there is some kind of a temperature aberration. The driver would also get to know about what has happened, and the action that they have taken can be updated onto the blockchain system for everyone to see, right? Then of course there are government regulators who need these details at a product unit level. They need to make sure that if there is anything which is going wrong with the COVID vaccines, they should know what was the reason for it, who was responsible for it, what went wrong, when did it went wrong, and how do you replace the products which have gone bad with the products which are perfectly fine. And of course, the end is customer. You can, so this solution also came with a mobile app. So what the customer can do is there would be a barcode on every single vial of COVID vaccine which is being administered, right? So they would just use the camera on their phone to scan that particular barcode, and they would be able to view the temperature history of that particular vial starting from the point of manufacturing till the point of administration, right? So now you don't have to trust the hospital. You don't have to just only trust the hospital. You have all these details available right in front of your eyes in your mobile phone, right? So that is how this solution utilizes IoT and blockchain, and it is being used to solve a very prominent problem of COVID vaccine tracking today. Moving on to the next slide. This slide explains why is it such a great idea to integrate blockchain and IoT. I read somewhere that IoT feels and blockchain remembers. So that is the scenario. There is data security. Every data transaction which is coming from IoT device can be placed onto a blockchain-based system. There is no way that this data can be tampered with, because you can use advanced methods such as cryptographic methods in which the data immediately emanating out from the IoT device gets encrypted by using SHA-256 algorithm. Device can be authenticated, because what will happen is now that the certificate, the X509 certificate, which is used to authenticate IoT device, will be used to create a public key and will be used to create an address for that particular IoT device. So there is no way that you can tamper with this now. immediately after integration of IoT and blockchain, your entire network becomes hardware agnostic, because blockchain does not have any hardware requirement. It can connect to any device. As I mentioned, it can be IoT device, a mobile phone, or a ERP system. There is resilience in your network because all of these nodes are running independently, and all of these nodes are putting in their efforts in order to make sure that the network runs smoothly and there are no issues. There is, of course, efficient firmware management, because there have been attacks on IoT devices wherein the requirement to update the firmware on IoT device becomes a point of entry for the malicious players into the network, right? So what they will do is they will create some kind of backdoor entry, or they will create Trojan horse viruses, and then they will update the firmware devices, and then they will start getting data from these IoT devices from the tampered firmware. Cost reduction, of course. Let's say if there's an organization which has manufactured IoT device, it is not required for that particular manufacturer to deploy these IoT devices and create a system of data gathering from these IoT devices, right? You have a blockchain based system, or a Ethereum or a Quorum based system which is run by multiple nodes. There's a new node which wants to deploy IoT device. They will simply purchase the IoT device and integrate it with their node. They don't really need a centralized system there. Process automation. I was talking about, creating logic using Solidity and putting that logic on a blockchain system like Ethereum. The program which gets written and deployed on Ethereum is called smart contracts. So I can deploy smart contracts, which says that, okay, I have ordered, let's say 50 vaccines with a specific pharma company, and there is an IoT device which tracks these 15 vaccines. The moment all of these vaccines are received by my hospital in the temp, and all of these 15 vaccines are have been transported in the temperature range which was required, there would be a logic trigger through which money will be automatically paid to the manufacturer of the vaccine, right? So this is a very simple and a very crude example of how things can be done, but then there is a lot of logic which can be built into these kind of distributed systems, and that is how IoT devices can be used in a better way. And there is always a historical data access, right? So today I am using a specific IoT device. Tomorrow, if that device is replaced by some other device because that device has gone wrong or something has happened in between, the data sets which were received from the specific device before would be stored onto this blockchain based system, and there would be an end-to-end traceability of every single data point, every single device, every single entry which has gone from a device to the network, right? So these are some of the aspects which make the match between blockchain and IoT a perfect match. And I think, yeah, so this was all that I had for this particular session. I am open to questions now.
Participants, if you have any questions or queries regarding the session, you can ask sir, Pranav Pathak sir. You can also type in the chat box also. So please ask the participants if they can, or if you can unmute them, or you can just turn their camera on.
You are allowed to unmute yourself. Participants, please unmute yourself and ask questions if there are any, or write in the chat box and I will read it up. Sir, on the other hand, I have a question.
Sure.
In IoT is very resource constrained.
Right.
So blockchain is a distributed ledger technology, we can say. So, but even then, on the edge side of it, I find it hard to visualize how we will implement the ledgers there.
Right.
Because in some servers we can do it. So can we implement proxy servers too?
Yes, so that's a brilliant question, and that's a very relevant point that you just brought up. There was one point which I actually missed while I was talking about blockchain. There are essentially two types of blockchain nodes, right? So one node is a complete node that will store all the information about, that will essentially store all the transaction details. The nodes which I was talking about, which have about 236 GB of data. These are computation heavy nodes, and these are involved in the actual computation, verification and validation of data transactions. There is another type of node which is called light node. Now these light nodes do not need to host or do not need to copy this entire data set, and they don't need to participate in the verification and validation. These light nodes are very light, as the name suggests. They can be installed on a mobile phone as well, right? Something which is as simple as a mobile phone. And then you can have IoT devices linked to either a light node, which is installed on a mobile phone, or you can also have IoT devices linked to, a full node, which is a full-fledged PC, right? So totally depending on what is the resource constraint and what is the requirement for your particular network, these devices can be configured. So all that you need on the IoT device is the X509 certificate, right? And the ability to send data on internet. If you have these two things, you can attach and link it to any blockchain network that you want without worrying about the resource constraints.
And how will the authentication take place for the device?
Right. So I do not have a very strong background and I don't really code as well. But then what I can explain to you is that every device has a X509 certificate, right? Now what happens is that when there is a registration process of that device on the network, right? So when the registration process is taking place, what you will do is you will take the X509 certificate of the device, create a private key out of that particular certificate, then create a public key and then create an address, right? So essentially and then tomorrow when the device is sending the data, this data will be linked to the private key of the device, right? So the verification process that we were talking about previously, you have a digital signature and you have the public key. So the other nodes of the network will get to know the digital signature, which has the message which the device is sending, and the public key of the device. So the verification that they will do is they will say that, okay, this is the digital signature, this is the public key. The device which has created this digital signature has the same private key which was used to create this particular public key, right? So that is how the verification works.
Okay. Thank you, sir.
Welcome.
Okay, then I think that's all because we have to running out of time and we have to conduct a test also. So you can just thanks, sir.
So we thank
Please go ahead. Yeah.
bottom of our hearts for taking time from your busy schedule to teach us today. We look forward to our next interactions very soon. Thank you very much, sir.
Sure. Thanks a lot. Thanks for your time as well.
Pranav, thank you so much. I am just extending my words to you for at the time and at the 11th hour, I have just called you. And I just want to know the participant about the industrial applications in which IoT was IoT application industries. So you have shared a lovely COVID tracking, COVID vaccine tracking system that you have designed. And it's a protocol. It's a, I think.
Right. So thanks a lot. This was a pleasure interacting with the faculty members, and I really hope I can meet all of you physically the next time I'm in Bhopal. It would be an absolute pleasure to do that. I will be happy to share the slides as well, which I will do after we have logged off.
Thank you.
Okay. Thank you so much. Thanks a lot. Have a nice day. All the very best. Hey, so I can leave the meeting now, right? There is
yes, Pranav, you can
okay.
Leave.
Thank you so much. Thank you so much. Have a nice day.
Thank you. Participants, I request you all to please switch on your camera because we have to take a snapshot of all the participants. And after this, we will be sharing the test link. So Tuhin and Priyanka, please go ahead and take the snapshots of all the participants presenting.
Sure, sir.
Yeah. Of all the, I thank all of you. Be a patient listener. All the 5 days you.
I request all the participants please turn on.
I think you all have been registered at AICT portal now, and the feedback link will be provided by the will be provided in AICT portal, ATAL portal, and you have to fill your feedback form over there. Okay, we are not providing you any feedback link, and the test will be conducted soon. This snapshot process is over, and you will be given 1 hour to take your test. And by Monday or Tuesday, we will upload your attendance and marks on the portal, and you can download your certificates then after. If you are having any queries regarding the FDP, you can just ask me right now about the process. How will you download your certificate, from where you will get the certificates, where we have to submit our feedbacks, anything. It all has to be submitted over the AICT portal. You have to just log in with your credentials, and you will see the feedback tab on the left hand side. You have to just fill the feedback over there. And without filling the feedback, you will not be able to download the certificate. This is how that portal works. Okay. So we will uploading your marks and attendance on the portal by Monday and Tuesday. Then after you can download your certificate, and we will keep you updating or posting on the group also, WhatsApp groups. If there is any delay or such, we will be keep you posted. और कोई query हो आपका तो पूछ सकते हैं मेरे को.
Sir, what about the recorded videos?
जी.
Sir, yes, what about the recorded videos?
That's the recorded video will be streamed on the YouTube channel of the department. The link will be also shared to you. The recorded video and the presenter, the faculty members and the industry experts who have consented to share the presentations will also be shared to you via Google Drive link or via mail.
Okay, thank you, sir.
Okay. Any other query you are having? So I think Priyanka, you can share that online Google form link that we have created for this assessment. The time limit is 1 hour, and you can appear for the exam. Good luck for the exam. It's not an exam; it's just an assessment test. It's a mandatory by the AICT to take the assessment test at the end of the last day of the session. So I am just providing you that link. Okay. And you all know that there is a AICT has asked about the minimum of 80% of attendance and 60% of the marks scored in the test. Those who have met out these two criteria, that is of the 60% of the marks scored and the 80% of the attendance, they are the only those who are getting the certificates. Okay. So these two criteria have to be met. 60% of the weightage of the attendance, assessment test, and 80% of the attendance. Okay.
I will share the link on the WhatsApp group and on this chat box.
Just in chat box also and the WhatsApp group also.
Yes.
Please you share the link.
Yes, sir.
Okay.
Yes.
Thank you so much, and good luck for your assessment test.
The link has been shared in the chat box, and I have also shared.
Okay.
Yes, I will also share on WhatsApp group also.
Yes, you can switch off your cameras. You can switch off your cameras and you can concentrate on your test. Please switch off your cameras and you can just.
The link has been shared on the WhatsApp group too, for those who are comfortable with that.
So I think that Tohin, you can just stop this recording and stop this meeting also.
Sure, sir. We'll stop the end the meeting.
And anything you just a minute. Anything anyone want to say about the workshop? Any?
Sir, I'm Kanakadurga, Dr. Kanakadurga from Acharya Nagarjuna University. So it is well organized and very informative and very interesting, and which will help in our career and as well as for our students also. Actually, I am from management department, but I have done MCA also. So I am interested to have this FDP. So I have attended this, and it is totally well organized, sir. Thank you. Thank you very much.
Thank you. Thank you, Miss. Thank you. Any other participant want to share their views about the workshop? They can share, because this is the formal valedictory also. Any steps and measures you want, let us know that how can we improve further? Feedback sort of. Okay, all of you are might busy with the assessment test. Thank you and good luck.
So shall I end the meeting?
Ma'am, stop the live stream and then recording, and then we'll.
Yeah.
Hello,
I'll stop.
ma'am.
Anybody want to say something? Otherwise, I will end the meeting now. You can concentrate on the.
When we have to give the feedback, any deadline for the feedback?
Ma'am, as soon as possible, you just.
The deadline for what, ma'am?
Feedback only. Feedback.
Feedback.
We are giving the.
No, feedback.
Yes.
Submit on the AICT portal.
Yes, now only.
Not now only. After the assessment, you can submit on the AICT portal.
Okay.
You can submit in a couple of days or whatever, and whenever you like.
Okay. Thank you.
प्रियंका भी मीटिंग ऐड मत करना, बिकॉज एक्टिवेट होगा ना आपका, जिसमें आपने लिंक दिया हुआ है. YouTube लाइव बंद.
जी.